So it looks like it's straight. So yeah, alright. I've stream here too. Uh-huh. Oh yeah, why not? Mm. Alright. So what am I doing? I'm studying linear algebra. And yeah, that's it. Basically. Alright. And 14 hours, okay, so alright, let's go. Hmm. And why is this? By the way. Wait, what's this? Oh, yeah, I'm actually doing it. Of course I am. Where is it? Of course I'm actually doing it. Yeah, where's the other guy? Who was he? Coffee, I think. No, I don't know who was the other guy who said he would watch every second. But yeah, I'm doing it. He'll come later, I guess. Alright, so let's go. I have enough for 18 hours with this, more than enough. So let's see. Where does it start? I don't know much about linear algebra, by the way. Only know, like, from high school, some basic stuff. So yeah, I have no idea what the curriculum form is. For example, I've seen it a few times in the tests. And by the way, I'm going to let's see, test in algebra first year exam. I want to compare my knowledge from the beginning of the stream to the end. Uh, let's see. So I'm going to try one of these exams. I have no idea about anything of the about anything. So yeah, let's see final exam. All right, no idea how to do this. Curriculum form, I have no idea what it is. No space, no idea. If the vector B is the sum of 4 columns of A, return the complete solution to A x equals B. Hmm, well, no. Let's see. I'm writing this with a mouse. Well, maybe I should do it here. 4, 11, and 21. And the matrix is what, 1, 2, 0, 1, 2, 4, 1, 4, 3, 6, 3, 9, and here goes another vector. What's the vector multiplication? 4 columns of A. So 8x equals 3. This is 3 by 4. This is 3 by 1. So here it should be 3, no, 4 by 1, right? I think. Yeah, never mind. I don't even know. I don't even remember that. Yeah, let's forget about it. I'll just start with this. Okay. So where is it? How to use this book? I don't care. I don't care. Where's it? Where's the beginning? Linear algebra is a beautiful subject. Mm-hmm. Acknowledgements. So the link is here. So if anyone watching the stream later on YouTube wants to read this, well, here it is. Alright. Systems of linear equations. We will motivate our study of linear algebra by studying solutions to the system of linear equations. While the focus of this chapter is on the practical matter of how to find and describe these solutions, we will also be setting ourselves up for more theoretical ideas that will appear later. So what is linear algebra? Okay. Multivariable calculus. I hope I don't have to use that because I have no idea about multivariable calculus. I think linear algebra comes before calculus, but it isn't really needed either. It's just like it's better to know linear algebra, at least the basics. Alright, so yeah, these equations are linear equations. Uh, so yeah, this is basic algebra for now. Yeah, no exponents or anything. So linear algebra is all about this, but how does it get this complex? I mean, okay, page 16. So let's go to page, I don't know, here. What the hell is this? Why do we need all this? Like, come on, what the fuck is this? Uh, all of that just for solving these. I don't know, I want to know what's the secrets to this. Like, why do we need all that? So, yeah, no multiplying variables or dividing or anything. And no trigonometry. Alright, that's fine. Occasionally, a square root. I didn't know that. Mm-hmm. CNO. Oh. Oh. I'm going to be using complex numbers. Hmm. Alright. I'll just. Uh, I'll just try to see if there's anything here I should know. Alright, yeah, this is fine. This is multiplication. Okay, this seems easy. Uh, okay, alpha and beta are equal if okay if the real part is the same and the complex part is the same. Fine. Okay, multiplication. Yeah, I mean this is AC. Wait, what? A times C minus B times D. Oh, I see. Yeah, yeah. Because BI times DI, of course, I squared is negative 1, so and AZ plus B. Okay, okay. Uh, okay. Alpha plus beta equals beta plus alpha. Nothing, nothing way different from real numbers here, so it's okay. Distributed one. Okay, so 1 is equal to 1, and 0 is equal to 0. Good to know. Alright, fine. Nothing too weird that I should study there, so let's just go. Uh-huh. Alright, so that was here. So however, there are many new algebras to learn and use, and likely linear algebra will be your second algebra. Well, it is. Like learning a second language, the necessary adjustments can be challenging at times, but the rewards are many. We have, it will make learning your third and fourth algebras even easier. Groups and rings, yes, I've heard of them. I know there's group theory. I don't know anything about group theory. I just know it's about closed groups under addition and subtraction and all that stuff. I know just that. Okay. First, have to learn a new algebra and realize that some of the old rules used for real numbers may no longer apply. Yes, I know. I hope that's not a problem. Okay. When do we get to everything? Please. Further straight, whatever. Look through all of the details with pencil and paper. I work through it with paint and mouse. I try to make everything as straight as possible. 1 plus 2. It's going to be a mess. Let's see how I can make this matrix. Eh, good enough. Okay. Suppose you're the production manager. Wait, no, I missed something here. Do you believe all the assertions? Okay. So I have to understand everything. Yeah, that makes sense. Mm-hmm. Alright, I will try to understand everything. It shouldn't be too complex. I mean, it's the beginning. Suppose you are the production manager at a food packaging plant and one of your product lines is trail mix, a healthy snack popular with hikers and backpackers, containing raisins, peanuts, and hard-shelled chocolate pieces. By adjusting the mix of these three ingredients, you're able to sell three varieties of this item. The fancy version is sold in half-kilogram packages uh at outdoor supply stores and has more chocolate and fewer raisins, thus commanding a higher price. The standard version is sold in 1 kilogram packages in grocery stores and gas station mini markets. The standard version has mm, roughly equal amount of each ingredient. It is not as expensive as the fancy version. When the bulk version is sold in dense grocery stores, yeah, there's a lot of text. More raisins and sells for less. The version of items able to receive and store 380 kilograms of raisins, 500 kilograms of peanuts, and 620 kilograms of chocolate pieces. Alright. How much to mix every day? Up to 1500 kilograms of raw ingredients. The most productive you will likely to be the most productive you will need to produce 1500 kilograms. And you prefer to not have any ingredients left over. Alright. So here we have the fancy, more chocolate, and less peanuts. Then this one has about the same when it's raisins. Yeah, including raisins, okay. And this one has more raisins and peanuts. And all the quantities are 15 to make it fit nicely with 1500 kilograms. So, okay, and you have uh, this amount of each thing. And what? So it's asking, how do you produce all the chocolate in here so that you spend everything, if that's possible? And all you can decide is how much to make of each of these with this. So yeah, it sounds like linear algebra. It sounds like one of those systems of equations. But here it is. It's right here. Right. B is bulk, standard, and this is fancy. Can I make negative quantities of each mix? Alright. And if we want to consume all of our ingredients each day, the storage capacity is listed here in our equations. Alright, so yeah. What's this? Okay. So resins, this corresponds to this. Okay, so what this means is, I guess, 7/15 go to bulk here. Wait. Okay, so mm, okay, so if you add all of these equations, you get 1b, so 15/15 v, 15/15 s, and 15/15 f. So that's like all the ingredients you need for bulk, all the ingredients you need for standard, and all of the ingredients you need for fancy. And you get 1500 kilograms. So this is separating them. Okay, let me think about this. Okay, let's read a bit more. It happens that this system of three questions has just one solution. Okay, yeah, that makes sense. Also, your job is easy since there is but one way to use up all of your raw ingredients making trail mix. Single solution is this. Yes, I understand why there's one solution. But wait, I need to understand the logic behind the equations here. Okay, so resins. Yes, this is resins. So 7/15. Alright, yeah. So I understand now. So you have B is bulk, S is standard, and fancy is fancy. I mean, F is fancy. So these are all the quantities you have to make. And here you don't know them yet. So what you're saying here is that 7/15 of the quantity of V is going to be resins. 6/15 of the quantity of standard is going to be resins. And 2/15 is going to be fancy. 2/15 of fancy is going to be resins. And that's all the resins. If you want to spend all the resins, you have to spend all the ingredients, right? So then that has to equal 380. So here you are making it so you spend all the resins in these three, but there are many ways to spend all the resins in these three. But if you do the same with the peanuts here and the chocolate here, then you can you can only have one solution. And I understand that. I don't understand that super rigorously, but I know that if there are as many equations as variables, usually there's only one solution. There could be zero or an infinite amount of them. I know that has something to do with the rank, but yeah, let's just leave that for later. That's just some of the bit I know about linear algebra. It's simple for you to verify that this is indeed a solution. I'll trust this. I won't try it myself. Okay, yeah. Determining solutions such as this and establishing that they're unique. The main motivation for our initial study of linear. Okay. So we have solved the problem of making sure that we make the best use of our living vector space. You must report weekly to the CEO of the company. You know he will be more interested in the profit derived from your decisions. So you compute. Alright, yes. So this is the cost. You take 300 kilograms of weight. Yeah, right. you have 300 kilograms of fence of bulk. So 7/15 are bulk, right? And wait. Okay, so you multiply this by 7 to calculate the profit. Wait. You multiply this by 7, you multiply this by 6, and you multiply this by 2. And you add them together. And, oh wait, no. It's here already. The average cost per kilogram. Oh yeah, then it's easy. Then you subtract these two, and multiply them by 300, right? So yeah, this is what's happening here. Fine. Then you got the daily profit. It looks like a linear computation, yeah, I guess. Things do not stay the same for long enough. The marketing department has suggested that your company's tail mix plus standardized on every mix being 1/3 peanuts. And it changes everything. So yeah, this is the second. And now this has infinitely many solutions. Alright, okay, I guess, fine. Alright, the format messed up everything. Suppose if kilograms of fancy mix. Okay. B equals for and S equals choices for any value of F. What is the operation schedule that shows so simplifying that. Okay, so it's already substituted here. 4F minus 5F. Yeah, I'll trust this. I'm not going to do this right now. I don't care. It looks painful to do on paint anyways. Convince yourself that these expressions for BNS, so still very infinite number. Yeah, I'll trust it. I've 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 seen this. This isn't too complex. But although values of s should probably be integers, yeah. I don't think that's linear algebra. I think that's Diophantine equations, and I'm not going to get into that, at least for now, because that gets really complex. I've seen like one problem that looks really easy, like a Facebook problem that could be for some moms on Facebook, but it's actually like even 99% of Harvard still be able to do it, or something like that. Like it's absolutely ridiculous. But it's always not like Fermat's last theorem or some bullshit like that that only like 5 people can do. Particle matter there are not infinite number of solutions. Yeah, okay, so positive quantities of the bulk requires that this v equals v this is 2f is greater than that. Alright, yeah, true. It can't be negative. That's doable, okay. Okay, so f has to be here. Nice. That looks better. 156 choices. Um, use the biggest possible profit for the company. So you compute an expression for the profit based on your S, uh, on your as yet undetermined decision for the value of F. So whatever F is, you're just doing it, and then you'll maximize it later. We don't know what F is, but you're calculating the profit based on F. Okay, so whatever F is, and we get that the profit is this. So F is negative. So increasing F will only decrease the total amount. So the more fancy, the less profit. Okay, so the lower F is, the better. And we have these possible solutions. So of course, 825 is the best. And then you have more profit, but you have stopped making bulk. Alright. Well, fuck bulk. All my homies hate bulk. Now what? No, okay, yeah. So we got rid of bulk, guys. Good job, CEO. Mm, now they want to charge less. Uh, you change this a little bit. Now this is 25 cents less. And just that change makes it so that now it's actually better to do. Oh my god. And just that 25-cent change gets rid of standard. It gets it just nukes standard. Alright. Just that 25-cent change. Another 540 kilograms of bulk. Bruh. What the profit is less. Nah, whatever. Measurement, I don't care. Give me the linear algebra already. I don't care about this. Come on. Uh, okay. Finally, some exercises. Is the equation linear or not? Well, I mean, what do you think? I don't know, man. I think not. Find all the solutions to system two linear equations. I do this. I do it. I don't care. It's not that hard. Debate and x minus y equals 6. Um, this, like that, yeah. Uh-huh, like that, maybe, okay. So how do you do this? This is just I'll just multiply this by 2, I guess. 2, 12, okay, so, and now subtract them, so you get 0x. Uh, plus 5y equals negative 20. So y equals 4, negative 4. And then if you remove this and make it so that this is -4, so this would be -8, so this turns into a plus. Now you do -8 here, 2x equals 4, so x equals 2. How the production manager might explain the importance of the, oh wait, actually it's 4 minus 12 equals -8, and 2 minus -4 equals 6. Yeah, it works. Describe how the production manager might explain. Wait, I'll check this out. Is there anything here? Nothing. Okay. Alright. Anyone here? Oh, you're still here. You're still here. Oh my god. You're going to learn linear algebra too with me? Uh, okay, so I might leave soon. Okay, it's okay. I don't expect it. I don't expect anyone to be here for like 18 hours really. Uh, uh-huh. Describe how the production what? Describe how the production manager might influence of the procedures described in the trail mix application. Well, if you don't do this, you get less profit. What am I doing? Uh, what happened? Alright, yeah, that's how you could explain it. Hey CEO, this is quite painful, says JJ. I mean, this is only the beginning. This is page 21. This is page 21, and like the first 15 pages are just like acknowledgements. Your audio quality kinda sucks right now, yeah. I know. Check this out. Do you see this? This is actually my phone. This is an app to make my phone the mic. So yeah, my mic is my phone. It actually sucks, but it sucks way less than my laptop's mic. With my laptop's mic, you wouldn't even understand anything. At least I think this is understandable a bit, maybe. I hope. Oh wait, these weren't the exercises. Wait, what? The example? No, I'm not going to spend any time here. I don't care. I want to get here already. Alright, so we will motivate our. Wait a second. Let me do something. Uh, okay. Okay, fine. Let's go. Are we finally starting here? Please. It looks like it. We'll motivate our study of linear algebra by considering the problem solving several linear equations simultaneously. The word solve tends to get abused somewhat, as in solve this problem when talking about the equation. When talking about equations, we understand more precisely. Find all the values of some variable quantities that make an equation, or several equations simultaneously true. So systems of equations, okay. Well, systems of linear equations. It has two questions. The first is not linear. Yeah, this circle here is not linear. Okay. These are both solutions. Sure, okay. We also need to also convince ourselves these are the only solutions. See this plot each equation on the xy plane. I mean, I could open Desmos, maybe. Let's do it. Desmos. Okay, check this out. This is a circle. Look, wait, what? No, 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 no. Wait, wait, wait. No, wait. X squared plus y squared equals 1. Now there's a circle. And we have negative x plus root 3y, negative x plus root 3y equals 0. Equals 0. And of course, it has two solutions. I mean, it looks like it. I don't know the exact value of root 3 over 2, but I don't know. Seems fine. Seems just about it. Mm. The origin with radius 1 and a straight line going through the origin with slope 1 over root 3. Yes. Yes, exactly. The sections of these two curves are of the size simultaneous solutions. The solutions we know are indeed the only ones. We have to resolution as sets. Okay. Now solutions will be sets. Fine. Usually in math tests, I just write them like in a square and that's it. Like here's the solution. In order to discuss distance of linear equations carefully, we need to process definition. Proof techniques. Ooh. Now we're proving stuff. This isn't like school anymore. Okay, so let's go. The first proof technique. Oh, wait. Uh, on page 23. Page 23. This page 23. It's page 23. So, okay, let's go here. Let's see what this is. The proof technique. Okay. A definition is a made up term. Is a concept. Okay. Okay, makes sense. This is just about definitions. What's the proof technique? Okay, equivalent definitions. Fine. Mm. Wait, this is just defining definitions. Uh-huh. If this, then that. And if that, then this. I mean, not necessarily. Well, I guess it depends. Depends on how you word it. Well, if you say if and only if, then yes. But if you say if, then no. Anybody, including you, can make up the definition. It has to be useful for describing interesting or frequent situations. Alright, makes sense. Only make nouns and adjectives. Okay, fine. There's a full list of all the definitions. Ooh, nice. Can you formulate the precise definition of what it means for a number to be odd? Well, if it's not even, it's odd. Oh, oh, okay. Didn't you just say it's the opposite of even? Hmm. Well, n is odd here. 2n, like 2k plus 1 equals n. So k plus 1 equals n for some integer k, I guess. Yeah, that's fine. Isn't that the definition you should use? I think it is. Can you employ your definition to test an odd and an even number for oddness? Well, if you have 2 here, then you have the 2k equals 1. This doesn't exist. So yeah. Okay, I'm going to look here just a bit. And this is just okay. And here I can click any definition. So this, for example, okay. I'm going to go back to page 23 and let's go. Definition: system of linear equations. Selection of m equations in the variable quantities x1 to xn. So these are all variables. We aren't using x, y, and z anymore because we have a lot of variables now. We will have a million variables and we don't have enough filters for that. And each one has its own coefficient and its own solution. Okay, the values of all a's, a, I, j, and bi, and xj, well, it's x of j, okay, whereas between 1 and m, okay, so basically all the a's you see here and all the b's are complex numbers, yeah. We will stick with real numbers exclusively, okay, that's fine. And sometimes only work with integers, yeah. I hope. I don't want to multiply. I should probably bring out the calculator. I don't know. Okay, let's see. Now we make the notion of a solution to the interesting precise. Here's the solution to the system. It's an ordered list of n complex numbers named, well, s1 to sn, so that if you substitute s1, well, each one with its corresponding variable, then for every equation of the system, it will work. Alright. of course. So the set of possible values of x1 to xn in order. Okay, yeah. It's an ordered set, of course. Did we write solution in a form like this? Okay, okay. Wait, right, fine. So what do we? Oh, okay, there's more set set theory. Uh, just basic set theory. Definition SSSLE. Solution set of a system of linear equations. SLE, SSLE, SSSLE. Yeah, that's going to help. The set of all, well, the solution set is the set of solutions. Okay, can be infinite or have nothing. Fine. Okay. So given the system of linear equations, this, we have four variables and three equations. And well, these are the coefficients. Convince yourself that this is one solution, but yeah, there should be an infinite amount of them, right? There are more to be found. Yeah, there should be an infinite amount of them, right? Um, okay, possibilities for solution sets. What's this? Wait a bit. Mm, okay, okay. Possibilities of solution. Okay, so what's this? Samples illustrate the possibilities for the solution set of a system of linear equations. So we have system of two equations. We'll get two lines by plotting this. Okay. They have one point in common. In the geometry, we believe this is the only solution. Of course. And now we change the second equation and they are parallel, right? Wait, oh yeah, they're the same. They're the same equation. This is the same but multiplied by 2. One more minor adjustment, changing this, and now they are parallel. Now they are, okay, yeah. Now they have no solutions. And these are all the behaviors, okay. Um, Example, STNE. I'm getting, wow. There are just so many abbreviations. Okay, this. Yeah, fine. I'm not going to learn all this. What the hell is this? Why? Example, oh yeah, the circle one because it's not linear. Okay, fine. Theorem, yes, oh yeah. I'll see that later. Coolant systems. Mm-hmm. Okay. With all this talk about finding solution sets, might be ready to begin learning how to find these solution sets yourself. Okay. Equivalent systems. Two systems are equivalent if their solutions are equal. The solution sets are equal. Notice here that the two systems of equations could look very different, but still have equal solution sets. Okay, fine. Okay. Alright, I didn't know this. Alright. Okay. Definition we can begin to describe our strategy for solving linear systems. Given a system of linear equations that looks difficult to solve, we would like to have an equivalent system that is easy to solve. Well, actually, it makes sense. Yeah. The system will have equal solution sets. We can solve the easy system and get the solution set to the difficult system. Here come the tools for making the strategy viable. Okay, equation operations. The following three operations will transform the system into a different one, and each operation is known as an equation operation because it changes nothing, right? So the equation of two equations, okay. Multiply each term of an equation by non-zero quantity, okay. Makes sense. Multiply each term of one equation by some quantity. Net these terms to a second equation of both sides of the equality. Is the first equation the same after this operation? But replace the second equation by the new one. I've heard about this. Okay. I've heard about this. This is like some cows stuff. It was like, yeah, something. I learned it in like matrices. So it applies here. There should be a theorem here. I don't know. This expression should be vague with the proof of the example that following should make it clear what is meant by each. Yeah. Uh, Stop and read proof technique T first, okay? So proof technique T, the mathematics about understanding theorems in understand. Fine. It's just what a theorem is. Uh, it's not a proof technique. Why is it in proof technique? Theorem we're about to prove conclusion is that two solution sets be equal for two systems. No, wait, are equal. What for two? You are being asked to show that two sets are equal. Wait. Oh, wait. What the definition is this? Oh, yeah. Are you kidding me? I mean, couldn't whole thing. So I really have to click everywhere. So already have to section SET, oh no, set. Section SE, set equality. Okay, fine. They have the same members basically, right? Hmm. Okay, okay. Okay, that means okay. 26. Okay. Easy. Okay, so the following criterion is rather long proof. Skipping the first reading. Going back to them when you are more comfortable with reading and studying proofs. I don't care. Let's read it now. Question operations preserve solution sets. Yes, I hope. We apply one in the original system and the transform system are equivalent proof. We take each equation operation and show that the solution sets of the two systems are equal. In the definition of set equality, of course. Saying statements are obvious. In this case, should be. There's nothing about the order in which we write in the equations that affects their solutions. The solutions will be equal if the systems only differ by a rearrangement of the order of equations. True. Okay, that was the first one. That makes sense. So suppose alpha is a number. Just a number. All right. Yeah, I hope it's a number. Let's use to multiply terms of equations I by alpha to the new system of equations. So now everything is multiplied by no what? Oh yeah, it's one equation. Let S, the solutions to the system. Okay. Let T denote the solutions to the transform system. So that S is a subset of T. Okay, let me put this here. Wait. Okay, there. Okay, suppose x1 is equal to beta. Okay, so we have all betas here. Here in the ith equation, we know it makes all the other equations of the transform system true. Yes, because the only one that changes is the I. So of course, we also know that this is equal to bi. So we can multiply by alpha and get this. So this is also correct now. Yes, correct. The equation of the transform system is also true. So we have established that this is a member of T exactly. And therefore S is a subset of T. Wait, what? Is a solution. Wait, what? Alright, right. Okay. Now we show T is a subset of S. No beta is subset. Okay, now the beta is a subset of T. Equation for we know it makes all the equation of the system true. We also know that alpha, okay, apply since so that wait, what? Oh, wait. We know it makes all the other equations true. Okay, yeah. Once I know that, it's a transform system. And the ith equation, okay, and we also know that this. Okay, yes. This is a solution to transform system, so yes, it is. Multiply by 1 over alpha, yeah, we get the same. Okay, the key point where we require that alpha is not 0, because what would happen if alpha equals 0? It just says 0 equals 0, so it just wouldn't matter. It would be pointless. And for the third one, suppose alpha is a number that is choose to multiply the terms of the equation. The term of equation y, no, I, by alpha, nothing to equation j. In order to build a new system of equations. Okay. Wait. Let's use to multiply the terms of equations I by alpha. Then I think the equation j in order to build a new system of equations. Okay. As denote the solutions, okay. I can't say much here. I just have to try to understand this. So we have alpha. Okay. So we have added the two equations. Suppose that's a solution to the original system. Learn the J's equation for a moment. Which makes all the other equations of the transform system true. It's a solution for, okay. Solution for the understand. Here in the J's equation. Yes, of course. Using the fact that the solution makes the I and J's equation true of the original system. Okay. We find that this is equal to this. Okay. Oh, alright, yeah. So alpha, okay, so this is equal to that, and this is equal to that. Okay, fine. Because that the J equation transform system is also true. So we have established that I'm going to there this is a member, so therefore it's a subset. Oh wait, yeah, yes, no, never mind. I get it now. So it works for every single beta, so it's not just this beta, it's like every set of betas. So okay, now this the opposite. This equation, so this is a transform system. So in the J's equation for a moment, makes all the other equations of the original system true. We now find that this okay is equal to this plus alpha beta I minus alpha beta. No, alpha bi minus alpha bi. And alpha bi is this. So right. We have everything. Now it's okay. So this is equal to wait. We don't find. Wait. Wait a second. The original system. This is a transformed system. Oh, alright. Yes. Yeah. Right. It's okay. Yeah, yes, I understand. The J's equation is true, so we establish that. Yes, of course. Why is not? Why is we not need to require that alpha equals zero, is equal to zero? Because if alpha is equal to zero, then you're adding zero to both parts, and nothing goes wrong. Okay, so that's it. And EOTSS. Okay, so this is okay. I see. So example, three equations, one solution. One that's the question two. Okay, so this is just what you okay, yes. This is Gauss. Mm-hmm. Fine. It's the only solution, yes. I wonder if oh I wonder they're all gone. Oh my. Hi. Sad. Why is this still going? Okay, is there any problem? Alright, it's fine, I guess. Wait. Okay. Okay. Everything is fine. Alright. Oh, what's this? Playback's 11. We're having a few people here. Okay, that's fine. Uh, what's going on here now? One, okay. Nothing, nothing wrong here. Yeah. Okay, so very unique solution. Okay, so this is just like middle school for now. Three equations, infinitely many solutions. Uh, why we choose this particular sequence of equation operations? Yeah, I think I can skip this for now. Just if you're watching this on YouTube, just like after the stream, then you can just pause, I guess. And of course, this becomes that. This is well. So this one is gone. And of course, this is I suppose A and B are this. Okay. The entire solution set is okay. So this is x1. This is x2, x3, x4. Yeah. Yeah. Right. Yeah. Screw this. Just where till we get to the new stuff, please. I want the cool stuff, not the stuff I've already learned. I don't want to skip anything just in case. See proof technique L. Is this like an actual proof technique now, or are you going to define something else? Um, the proof. Okay, fine. Science. Oh my god, what the hell is this? And yes, too. Okay. Again, science is almost man. Man, I'm not going to read all of this. Like out loud at least. Let me just read it quickly. Hmm. Okay. Okay. Speak slowly. Fine. Okay, can I get started? I know how to get started, but please tell me 教えてください。Uh, what is the statement of the theorem is an if then? Okay. Okay, 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 I guess. Where, where was I? Where was I? Reading questions. Questions as the system of equations. This. Explain your answer. Well, you see, if you multiply this by 2, you get the same thing. So it's basically just one equation. So I'll take this for example. I'll take this one. It's just like removing this equation. This one doesn't matter. So you have an infinite amount of them. On the solutions of the system of equations, this have explain your answers. This is the same times 2. It has no solutions because if you multiply this by 2, then you get this. This is the same as this. So if you subtract them, we're using the elementary operations like the what was it, the equation operations. Then you get 0 equals uh, for so 0 equals 10. So yeah, that doesn't work. And what do we mean when we say mathematics is a language? I don't know. You tell me. Find a solution to the system in example IS, where x3 equals 3 and x4 equals 2. No thanks. I'm not here for like simple the simple stuff. I want the cool stuff, the stuff I haven't learned. Each archetype. Solutions list. What? What? Dimension one null space. I don't know what you mean with that yet. I hope I can learn it today. But at this rate, I am not going to do it anywhere. Please. Where's the new stuff? One solutions to linear system x plus y equals. Where? I don't want the simple stuff, please. 3-digit number has two properties, the tens digit and the ones digit to 5. The numbers were then with the digits in the reverse order and then subtracted from the original number. The result is 792. Use a system of equations to find all the 3-digit numbers with these properties. The tens digit and the ones digit add up to 5. The tens digit and the ones digit add up to 5. So we have a number that is 100x plus 10y plus c. Okay, this is the number. So it's like x, y, c, where x and y and c are between, well, y and c are between 0 and 9, and x is between 1 and 9. Okay, where are we? Here. The tens lead and the ones lead up to 5. So y plus c equals 5. Um, what else? If the number is written with the digits in the reverse order, and then subtracted from the original number, the result is 792. So 100c plus then y plus x, and then subtracted from the original number. So we have 100x. Okay, so we have 99x minus 99c, and the 10y just disappears. It's equal to 792. 792, so this is the system of equations. I'm just going to do this like that, exactly. So like that. This is the system of equations. I'm not going to solve it. Oh, this is Mensa. It should be really hard, like for really smart people, I guess. But it's in page 33, which is more like page 10 or something. But sure. Find out of the 6-digit numbers in which the first digit is 1 less than the second, the third digit is half the second, the fourth digit is 3 times the third, and the last two digits from a number that equals the sum of the fourth and fifth. The sum of all of the digits is 24. No, that's just time consuming. I'm not doing that. Okay, sentence without has at least two meanings. Identify, wait, what's this? Identify the source of the double meaning. This has nothing to do, but sure. Write the sentences at least twice to clearly convey each meaning. They are baking potatoes. So some people are baking potatoes, or these people are baking potatoes. He bought many ripe pears, and apricots. So it could be ripe pears and apricots, or ripe pears and apricots. She likes his sculpture. She likes his sculpture. What? Um, what? I don't know. Yeah. I decided on the bus. So I decided on like getting on the bus. Or I decided something on the bus. Like, sure, whatever. She likes his sculpture, I have no idea. Discuss the different meaning. Why? Why? What are these changes? Like, what? The grammatical structure is meaningless. predict its faults, correlate ideas, sleep fiercely. What's this? What? Why is this in linear algebra? Okay, let's see what the D are. Something is D actually the formula definition means for. Okay, yes. What's your definition? I've already done it. Explain why the second equation operation definition it always requires that the scalar be non-zero. I've already explained it, I think. Oh, yes, finally something new. Reduced row echelon form, finally. Yes, finally. What's this? Matrices. For solving a few system equations, you will recognize that it does not matter so much what we call our variables. Okay, fine. An m by n matrix is a rectangular layer of numbers from complex numbers having m rows and n columns. So it's 3 by 4. We will use uppercase written letters to denote matrices. Okay. Okay. So for matrix A, the addition A sub ij would refer to the complex number in row I and column j of A. So okay. Row I, so this is I, and this is j. So here j equals 1, j equals 2, and here it's like, okay, so columns and rows, these are denoted by j, these are denoted by I. Oh my god, I'm so good at this. So it's like 1. Okay, let me get the other hand. This is 1, 1. 1, 2. And here's 2, 1. And it goes on, right? 3, 2, 3, 2, 3. Except, okay, yes. Oh, wait, I missed something. Do you think that this refers to the whole matrix? It does not. Okay. Chapter M. Why is there a chapter M? Oh, the matrix is chapter, okay. Yeah, that's like on page 200 or 300, so I'm not getting there. Sadly. Maybe I'll make another stream if for some reason people like this. Um, okay. Mm, okay. Was doing something? Okay. With the equation operations is the equation. Okay. The names of the variables are really important. It really does not matter. Okay, I get it. In this subsection, we will describe some notation that will make it easier to describe linear systems. Okay. Column vector. Okay, let's see. It's another list of m numbers, which is written in order vertically, starting at the top and proceeding to the bottom. At times we will refer to a column vector as simply a vector. Column vectors will be written in bold, usually with lowercase Latin letters. On the end of alphabets, okay. U, V, okay. And with arrows, of course. Refer to the entry of component of the equation I. Yes, since it's just the line, I guess. Alright. Serial column vector. Serial vector of size m is just all zeros, m zeros, in a column. Coefficient matrix. Um, for system of linear equations, the coefficient matrix is, well, the matrix of all the a's here. Okay, fine. And the vector of constants is the vector of all the b's. Alright, fine, fine. The solution vector is all the x's. Okay, so solution vector of size n, of course. So it's different than this in size. This has size m, and this has size n. Okay, uh, okay. So matrix representation of a linear system. Ooh, if A is the coefficient matrix and B is the vector of constants, what is fancy L? What's this? Just an L? Okay, okay. By the way, let me just do this. It's a shortcut the expression for the system of linear equations, which we would refer to as the matrix representation of the linear system. Okay, so LS, linear system, AB. Okay, so A is the matrix, the coefficient matrix, and B is the solution. No, the B is the constant vector. Yeah, the vector of constants, okay. So this has a coefficient matrix like this, the vector of constants this. It will be referenced to as this, okay. LS A of B, okay. So linear system AB. Augmented matrix. Ooh. The augmented matrix of the system equations is the n times n plus 1. Okay, so it's just this, but adding this to the end, adding b to the end. Okay, the augmented matrix represents all the important information in the system of equations, since the name of the variables have been ignored, and the only connection with the variables is the location of their coefficients in the matrix. It is not important to realize that the augmented matrix is the matrix, and not a system of equations. Exactly. An augmented matrix always belongs to some system of equations, and vice versa. Okay. So this, so the augmented matrix is this. Okay, so what's the echelon form then? Is it this? Is it just the matrix? Is that it? Is that really it? Was there really a question in the test I saw about writing a matrix in the echelon or something? Is that it? Oh, okay. An augmented matrix for system of equations will save us the tedium of continually writing down the names of the variables as we solve the system. It will also release us from any dependence on the actual names of the variables. Mhm. So the equality operations, equation operations. Precise solutions, exactly. The next two definitions and the following theorem carry over these ideas to augmented matrices. The swap the location of the rows is the same as the first one. Multiply the entry of a single row by a non-zero quantity. Exactly, that's the same. We're talking about augmented matrices, right? I think. There were two augmented matrices, yes. Multiply the entry of one row by a Gaussian quantity. This is the same as the third one. Yes. Symbolic shorthand. Okay. So this means what? This means multiply the row. This means like this. Like substituting the jth row by this. Okay. Okay. Uh, okay, so zero equivalent matrices. Yes, this is just swapping everything and subtracting them. This. Wait, what? What? Equivalent can be seen from this. Oh, okay. And this. Okay. Can also say that any pair of these three matrices are row equivalent. Wait, someone pinged me. Alright, what do you want now? G. Tell him what? Dude, I'm learning linear algebra. It's about you being a fanboy. You have to prove you're a fanboy. Okay, what's your proof? I don't know, I didn't see it. I'm really stopping to see this. Oh my god. Okay. I mean, I'm an old member, but I didn't see that. So, I only saw Waffle's dick. Uh, we can also. Okay, so. The preceding definitions are the. Wait. Okay, okay. We can also say any pair. No, wait. Each of the three row operations is reversible, yes. The definitions are designed to make the following theorem possible. The row equivalent matrices represent system of linear equations that have identical solution sets, yes. It makes sense. Because they are the same rules, basically. The equivalent matrices represent equivalent systems. Suppose that A and B are row equivalent augmented matrices. Do I need to read this? I don't think so. I prove the affairs with the null exactly. Nice, nice theorem, bro. This is the theorem. This is the proof. They're the same. It's just the same thing. At this point, our study is to begin with a system of equations. Uh, system of equations represent the system by the augmented matrix. Perform row operations to the simpler augmented matrix. Convert that to a simpler system of equations, and then solve that system. Easy. Wait, let me try something. Can I? Oh, wait a minute. Can I? Can I write like this? So imagine I get this. Oh, I can't. I can't. What about this? Ooh, yes. So wait. If I do this, if I do this, do I get to like? Wait. Oops. Do I just? Okay, never mind. We were just testing something. Okay. The question is one solution repriced. Okay, so now it looks much better, of course, much cleaner, because we don't have these unnecessary numbers and letters, of course. And apply row operations, of course. So yeah, and then I'm going to check it. Of course, now you have this. Let's not forget that this is the augmented matrix. Okay, so okay, that's easy. Bro, this is just going to be such a fun stream for everyone watching. For like the three people that will watch for 10 minutes at most. The preceding example of mm, what is simpler from phonetics? Well, let's see. Definition of reduced row echelon form finally is reduced row echelon if it meets all of, so this is reduced form echelon, okay, finally. If there is a row where every entry is 0, then this row lies below any other row that contains a non-zero entry. The leftmost non-zero entry of a row is equal to 1. The leftmost non-zero entry of a row is the only non-zero entry in its column. Wait, what? The the leftmost non-zero entry of a row is the only non-zero entry in its column. What? Okay. Considering it's two different leftmost non-zero entries, we're located in row I, column J. One located in row I, column J, and the other located in row S, column T. Okay, I need to draw this. This is getting pretty weird. Okay, please. Okay, so if S is greater than Y, so if S is okay greater than Y, T greater than K, so we have leftmost non-zeros. So like uh, so I just name them A and V, and this is 0, 0, 0. Yeah, just like that. Hey guys, and this is whatever. A row of not of only 0 entries is called a 0 row. Wait, what? Wait, is this it? Of course, of course. So it means that if S is greater than Y, so the lower it goes, the more it goes to the right. So this can't be here. Like, okay, so say that okay, that's horrible. So say that this is B, that this is C, this can't be C. Just S is greater than I. Wait, row S, and this is row I, and row I column J. This is I J. This is okay. So if this is in a lower, okay, so this is in a lower row, it can't be under it. So now this is all zeros. This has to be zeros. 0, 0. Okay, so this is row. I didn't. Okay, so I knew this. I just didn't know it was called the row echelon form. So this is it. Okay. Okay, fine. So this is in row echelon form. Yes. This is row echelon form. Mm, okay. The number of non-zero rows will be denoted by R. It is also equal to the number of leading ones and the number of pivot columns. What's a pivot column? Okay, wait. let's just do this. Oh, wait. The leftmost zero entry is called zero. Okay. The leftmost non-zero entry of a non-zero is a leading one. Exactly. Okay. A column containing a leading one will be called a pivot column. A column containing a leading one will be called a pivot column. Okay. So the number of non-zero, yes, so of course each column can only have a one, just one. Oh, wait. Which is also equal to the leading one. Yes. Okay. Set of column indices for the pivot columns will be denoted by B equals this set of. Okay, wait. Set of column indices also like the M, no, the J. Right, this is the I, this is the J. While the columns that are not pivot columns are denoted as F and Y. Alright. Why not? The principal feature. Oh, so we're not actually going to use DNF like this. Okay. Alright, so this is row echelon form. This is row echelon form, yes, exactly. The matrix has two zeros and the pivot column, three pivot columns. One, two, three. So this, okay. You see, not introduce a formal, okay. First theorem has a constructive proof. Okay, let's see what this is. I lost the page number. Conclusions of proofs, combinations of types of the theorem. We simply assert that something exists by building it. Okay. Okay, so where was I? 45. Oh, there's code there. Why is there code there? Matrix, precise matrix, then there's a matrix V so that A and B are row equivalent and V is in reduced row echelon form. Okay. Proof. Suppose that A has m rows and n columns. Okay. Should I do this here in Paint or what? A and B by a row operation. This procedure is known as closed-Jordan elimination. I refers to a row being converted, J refers to a column. So this is the I, and this is the J. And R keeps track of the number of non-zero rows. Here we go. J is 0 and R is 0. Wait, what? I mean, I know this procedure. Should I? Okay, so is J now equal? What's N? What's N? You mean R? No. No. It can't be. Entry of A column J rows R plus 1 through M. These are 0. Then go to step 2 and increase. Okay. Choose a row from rows R plus 1 through M with a non-zero entry in column J. These are okay, fine. Okay. Yes. Fine. The result of this procedure is that the matrix A is converted to a matrix in reduced-row echelon form, which we will refer to as V. When I prove this claim by showing that the converted matrix has the requisite properties of the definition. This first. First, the matrix is converted to row operations, so they are row equivalent. And the proof that it's in row echelon form is more complicated. Okay, so and there's this massive. Oh my god. Okay, and I wonder if there's anyone here. Is there anyone here? No, there's no one here. I'm alone. Oh, who's that? Sakamoto. Hi there. Well, yeah, hi. Alright, so, you're working in Python. Do you know linear algebra too? I mean, well, it's a what, so yeah, I doubt you need linear algebra, but it's like a Discord bot, I doubt it. Okay, so yeah, I'll just look at mute chat on my phone. I will just use your Steam as a kind of background noise. Alright. Okay, so let's see. Matrix A is being converted. Okay, so there's this massive text one. It's not really massive, but um, okay, where was I? The matrix only converted through row operations. Yes, okay, this was fine. Then as we begin step 2, the first j columns of the matrix are introduced row equivalent form with r non-zero rows. It is true at the start when j equals 0, since the matrix has no columns and so accurately meets the conditions of definition REF. Alright. In step 2, we increase j by 1 and begin to work with the next column. Okay, so there are two possible outcomes. So if all of the other, like, if, okay, so we have the first, this is the matrix. So if everything here is a 0, then just go to the next one. Okay, so that's okay. Uh, with no changes, we recognize that the first 8 columns of the matrix, the first row, okay. Suppose instead that the entry in row I of column j is not 0, then r plus 1, okay, so the first j minus 1 entries of this row are all 0. Wait, what? It's between, the first j minus 1 entries of this row, oh yeah, so like this, yes, of course. Wait, no. Okay, whatever. Do I even, there's actually code here. Wait, no, it's not code. What's this? It's pseudocode. Yeah, whatever. Look, I know what. I found this in school, like not even that long ago, maybe like 2 months ago. Uh, so yeah, this I'm not going to try to understand this. Okay, so notice that as a practical matter, the end, we can put it all together. Yeah, this I'm skipping this. I don't even care. I know this. Oh my god, what the hell is this? I see Greek letters already. I see a delta. Okay. Mm, okay. Almost every interesting property of a matrix can be discerned by looking at the row equivalent matrix in reduced row echelon form. Okay, fine. So further, it is important to know that matrix P is guaranteed to exist by theorem REMF. Okay, 46. It's 46. What's this? Oh, okay. Just that. So two proof techniques are applicable to the proof. Fill out and read two proof techniques, CD and U. Okay, let's see what CD and U are. So contradiction, okay, I know this one. should be simple. If A then B, so of course, if A then B, so if A is true and B is false, then if it fails, then we can prove that if A then B, of course. Then so we yes. Okay, this isn't anything I don't know. So I'll just skip it. And uniqueness. A theorem will sometimes claim that some object is unique. So there should be one of such object. To prove this, a standard technique is to assume that there are two such objects and analyze the consequences. The result may be a contradiction. Or that we use to prove a contradiction. Or just that the two different objects are actually equal. Alright, so now what do you want to show me? Reduced row echelon form is unique. Suppose that A is an n by n matrix and that B and C are n by n matrices that are row equivalent to A and in reduced row echelon form. Then B equals C. Wait, so okay, so if B and okay, so if B and C are in reduced row echelon form, then B equals C. Okay, it's bruh, what the hell is this? What the hell is this? I don't think I've ever seen a proof this long that I want to read it. Of course, I've seen like Fermat's theorem proof, or like that 1 millennium problem that was solved. I've seen that proof too, but the difference is that I have to read this. Okay, so we need to begin with no assumptions about any relationships between B and C, other than they are in reduced row echelon form and both equivalent, well, row equivalent to A. So if B and C are both row equivalent to A, they are row equivalent to each other. So repeated row operations and matrix combine the rows with each other using operations that are linear and are identical in each column. Key observation for this proof is that each individual row of B is linearly related to the rows of C. This relationship is different for each row of B, but once we fix a row, the relationship is the same across columns. Okay, so like they're proportional or okay, so more precisely, they are scalars delta sub ik, such that one. Okay, so ik are between 1 and m, such that for any I between 1 and m and j between 1 and n, b and j is equal to bruh. Bruh. This is actually ridiculous. Okay. Okay, I'll try. 1 is less than. Okay, so I and k. There are scalars delta I and k. So for any one. Okay, so for any I between 1 and m, and j between 1 and n. Okay, so we have that v I j, this is equal to, okay, this is equal to the summation from 1 to m of all the deltas delta ik times c kj. You should read, okay, it explains this a bit more here. You should read this as saying that an entry of row I of P is a linear function of the entries of all the rows of C that are also in column J. Oh, right. And the scalars, which are these, depend on which row of B we are considering. Of course. So, yes, so there's a delta. There's a delta here. So like delta I. So delta ik. Delta ik. Mm, okay. I think I understand a bit more now. So we have delta ik times C row k column j. So the C k j. Okay. Okay. Okay, I'm going to make these matrices here kind of, they should be the same size. Okay, this is into scale, I guess. And so we have b I j here and c k j, and then there's the, like, this, all of these c's, and then we have delta ik. There's, like, this is I, this is the I. Okay, this isn't like, okay, oh, right, alright, yeah, I understand now. I was thinking like the deltas are like, they're like in a line, like in a matrix, of course. No. You understand now, finally. Okay, this is gone. So, okay, so there's this relationship, right? So like you take this line, this is the line A, the line I, you multiply by some delta. This is a I K. Wait, now. So this is the j, and for this j we have ik, and it doesn't matter what j it is. This is the same delta. The delta only changes with the row. Okay, okay. So that's like saying they are row equivalent. Are you kidding me? Oh, this has to say they are row equivalent. Mm, this idea will be maybe more complicated now, but will be more familiar. Will feel more familiar once we discuss linear combinations, and also when we discuss row spaces. Okay, 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 fine. What's this? Okay, okay. This is an exercise. Why did you say this is an exercise? This is just the beginning. Oops. Okay, so the range of this experiment. Hmm. We now repeatedly exploit the fact that B and C are in reduced row echelon form. Recall that the pivot column is all zeros except a single one. Oh, wait a minute. Was it? Oh, yes, 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 yes. Right, right. Wait. Okay, here I am back. Back to this. So, if R is a matrix in reduced row echelon form, and D sub L is the index of a pivot column, then R sub KDL equals 1. Wait. If R is a matrix in reduced row echelon form, like this, there are like zeros here, obviously like zeros. And this sub L is the index of a pivot column. Okay, so we have that column. Then this is R, the matrix R. Then K, DL, oh yeah, DL equals 1 precisely when K equals L. What? Okay, okay, this is a mess. Mm. The DL is the index of a pivot column. Then R, K, DL. So 1 precisely when K equals L. So like when this is the diagonal. No. What? pivot column is all zeros. I don't understand. This sub L is the index of a pivot column. Okay, okay. This sub L. So the D doesn't matter, it's the L. The L, this is like the L. This is the same rows. We are saying the same. It has to be the same row and column number. But that doesn't make any sense. That was never mentioned. In fact, look at this. This is row echelon and has all zeros. Oh no. Alright. Never mind. It was referring to the index of a pivot column. So there might be columns here that aren't pivot columns. And then yes, K is equal to L. Of course. Yes. Otherwise it's 0. Okay. And also entry of R is both below the entry in row L, and to the left of column DL is also 0. Okay. So okay. Look at examples of matrices in the circle form and choose a leading one. The rest of with a box around it. The rest of the column is also zeros, and the lower left quadrant of the matrix that begins here is totally zeros. Yes, it is. Assuming no relationship about the form B of B, C, and no V and C, let V have R non-zero rows, and denote the pivot columns as D. Okay, the set B. Now for C, let R prime denote the number of non-zero rows, and denote the pivot columns as D prime. Okay. So there are 4 steps in the proof, and the first 3 are about showing that B and C have the same number of pivot columns in the same places. So R equals R prime, and D equals D prime. Right? Yes. First step. Suppose that D1 is less than D prime, than D1 prime. Okay, so 1 is equal to B. Okay, so this by definition of where was it here? Yes. And then so it was the same as this. Okay. And then and this leads to a contradiction. Alright. Because this is greater. So it's like move to the right. So this is a 1 in matrix B. And the 1 is here in matrix C. So this will be a 0 now. Okay. So, okay. The entries of C are all zeros since they are left and below of the leading one in row 1 in column D1 prime of C. So we know that D1 is greater or equal than D1 prime. Entirely similar argument, reversing the rules of B and C, we could conclude that D1 is less than or equal than D1 prime. So D1 equals D1 prime. Fine. So now we have determined that D1 equals D1 prime. Okay, so this is like induction now. So let's assume that we have a bunch of these up to P. Then we'll show that it will also work with P plus 1. So since we have 1, since we have it works for 1, then it will work for 2, and then also for 3, and then also for 4. So it will work for just for any number of rows. Okay, so um, so let's assume that isn't the case. Let's assume that d of p plus 1 is less than d prime p plus p of p plus 1. Um, okay, yes. So we have that 0 is equal to b p plus 1 dl. P plus 1. Wait, what? Wait, what? No, wait. Wait, I might have to skip this. This is just brutal. I've never read. I have never read a proof this absolutely ridiculous. Which is probably just pretty simple, but it's much more complex than anything I have done in the math Olympiads. Like by far, it's not even close. Bruh. This is page 48. Page 48. Okay, nice. Love to see that. Suppose that d, okay, d of p plus 1, d p plus 1. So, okay, so that's fine. For some L. No, wait. No, for some L between 1 and p, oh, dl. Alright. So this is 0. This has to be 0. Because this is like p plus 1. But L is at most p. So we are like, this should be a 1, but we can only get to this. This is all serious. Okay. So this means pay by the same wait, let me just find this again. Okay. Yes. So now we have this. So 1 to m delta p plus 1 k times c k dl. So according to that, and this is the same as with d prime, if it's also zero, since it's even greater, right? So of course, uh, this is equal to delta p plus 1. This is really hard, for me at least. From c l d prime sub l plus, what even is this? K is not equal to, okay, never mind. So we are getting the L out of this summation. And this is a C. It's a 1. This is a 1. Yes, this is a 1. This goes away. Oh, and all of the other ones are 0. So this goes away. And you get this. So delta p plus 1L is 0. How do you even find this proof? How do you even... So delta p plus 1L is 0. Wait, so delta p plus 1 comma L is this. What was p plus 1? Okay, so yes, let's say this p plus 1. No, well, yes, let's say this is p plus 1, and this is what's wait, now this is p plus 1, and the L is the index of the column, the pivot column. Wait, now this isn't matrix, this is the delta. Bruh, I'm spending so much time in this proof when I don't even need to. Like, come on. Okay, okay, okay. I might just actually just yeah. Okay, okay, never mind. Page 46. I think I'm just going to skip this. I'm going to give it one last try, one last attempt. Yeah, this is pretty ridiculous. Delta P plus 1L. Okay. I mean, I'm not this advanced in like proof theory. I haven't read many proofs. So yeah, delta P plus 1L. Delta P plus 1, I think, should be. So, wait. The delta is the number that multiplies this. Okay, so for each row of this, and for each row, okay, 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 yes, 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 yes. So P plus 1 here, and L in the C matrix. And that's 0. Wait, what even was L? L was like the index of B, right? No, 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 no. It's not. Wait, it is. It is. So between 1 and B. So we have that all of those are 0. All those deltas are 0. Wait, so if all the deltas are 0, then they are the same matrix, right? Uh, I don't know, I guess. Wait, no, no, it just be a 0 matrix, I think. I'm not sure. Whether 1 equals B, okay, plus 1 D, okay, fine, which equals this, okay, K D equals 1, fine. Wait, oh yes, was like that. Oh yes, yes. So okay, this turns into that. Uh, Also k equals p plus, that's just separating the summations. And this is a 0. Okay, so p plus 1. So if L is here below p, so yeah, according to this, now we have this only is equal to this is equal to this. How do you find this? Surely, how do you find this? How many years have you? Who found this? Like, surely, I don't understand how how a human can find this. It's absolutely ridiculous. I didn't expect to see this kind of stuff, which is probably pretty simple compared to the rest. I don't know. I hope not. Because this was absolutely. Ugh. And I was expecting to get to like page 100 or 200 maybe in 18 hours, but at this rate, I'm not going to get to even like 100. No, even though I'm only 52 pages away. If all of them are like this, I'm going to get stuck in like page 60. This contraction shows that of course, yes. So, an entirely similar argument, which I wouldn't read it again if you copied and pasted it. We would conclude that this, so therefore that. Okay, we have the induction done. That was pretty simple, I guess. Yeah, it was fine. You know what? I'm going to screenshot this shit and send it to lobby. I'm going to screenshot this. Screen. Okay, sorry, my laptop is lagging a bit, I guess. Because of all the streams, well, all the two streams, you see. I'm actually going to screenshot this. Like that. This looks so fun. Wait. Oh. Wait. 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 Wait a minute. Where is it? It's here. Can I? Oh, this is actually fine. Oh, I should. Make, okay, I'll add it here. On math. Let's see. Where is it? Where is it here? Uh, fun, bro. Everyone's going to want to join. Like the 7 spots are going to fill in no time with this. I'm going to send it to lobby. Has anyone said anything about this? I wonder. What's algebra? No, alright. Should I send this here? I'm going to do it. I don't care. Uh, fun. Oh yes, everyone wants to. This guy absolutely loves it. I know it. Damn maths, bro. Yes, of course. It's not like I spent like half an hour on this. No, not at all. Deserved donut. Okay, where was I? This. Oh wait, I don't want to skip everything. I don't understand a single thing. Yeah, you can't understand just by looking at this. I guess you need to look at everything. Anyone here? Yeah, probably. Uh, Apparently not. Wait, I go here. Wait, no. Oh, there is someone. What? Alright, whatever. But this is such a fun stream. I mean, where else do you get to look at so many sigmas in one screen? This is so fun. Okay, so this shows that we have that for every single L between 1 and R prime is less than R. Why is R prime less than R? What? Man, what did I do now? Wait. Uh, what's going on? How do I even restart the live chat? Okay. 1 second. Oh wait, no, not showing well. And why is this still 4? This should be going well. Click on pop about chat. What's going on now? I don't understand. Oh wait, now it's going well. Start chat. I can't see the chat. Okay, you know what? I'm going to just reload the page to see the chat. Okay, so Gambattene, maybe there's a video on YouTube explaining that equation with the hard one. You promised 18 hours. I'm doing 18 hours. I'm doing 18 hours. Right, is everything fine now? This should be fine. I hope. it should be. Well, this is good, so I guess it's good. I guess. Screw this. What do I even have? Okay. Just go to mute chat since. Okay, so oh, excellent connection. Perfect. Perfect. Fine. No, I'll just go on. So okay, what was this? Maybe there's a video on YouTube explaining that equation. What? This. This, I mean, how do you even search this? I, I, I don't know, man. I think this is pretty hard to search on YouTube. Like, you, you even need LaTeX to write it, just to write it. So I just won't. But thanks for the suggestion. You should read this. No, wait. Where was I? Okay, so this contradiction shows that. Okay, I was here. Okay, this is the third step. Right, I didn't see the third step. You know what? Everything should be okay now. I'll just pop out the chat like before and keep it like that. Hopefully. Wait, what? What's going on now? Okay. It's there. It's that's there. That's there. And there and there. And I'll give this here. Or maybe like that. Okay, so this should be fine now. Third step. Okay, back to the impossible stuff. Now we establish that r equals r prime. And r prime, what was r prime? R prime was the number of non-zero rows. Okay, the number of non-zero rows. Uh-huh. The number of non-zero rows. Hmm. But isn't that like implied or wait no? The non-zero rows, so like okay, these are all the zero rows. So here we have R. This is R. There are rows here. And R is supposed to be the same as R prime. So let's make. How could it not be the same as R prime? Alright, whatever. Let's just see the proof. So the arguments above, we know that all of these are the same. So let's assume that R prime is less than R. So there are more non-zero columns here. And wouldn't that mean that there are less D's? We wouldn't even be able to say this. But okay, whatever. So for one, less than or equal to L less than or equal to R prime less than R. Zero is equal to this, since we're in R. Um, okay, yes. The L. So like the pivot columns before R. So yeah, I guess. You know what? Yes. This I need to review it later. Even if I read it now and don't skip it, I need to review it later because it's a complete mess for me, at least. Like seriously, absolutely horrible. Okay, so let's see. This is equal to that. Okay, fine. Now we separate these two. Okay, that's fine. And since these we have this being two. Wait, no. Oh yes, 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 yes. K is greater than R prime. Then it's all zeros there, so of course this is all zeros. This is all zeros, so everything here disappears. So now we have this. This is equal to D prime R L, since they are the same. So so delta RL of C. So we take this one out. L, the prime L, of course, this is 1. And all of the others, since the R prime, no, the K changes, so all these have to be 0, of course, they have to be 0. So we have that delta RL is equal to 0. Delta RL is equal to 0, which would mean that okay, delta RL. Okay, let's just keep going with this. So delta RL, send the entries of row R of V. You can do it, I believe in you. Can I do anything with this? No. It's only, okay, so, I don't know, what this? Take a heart, I guess. Um, okay, so, uh, okay, so now examine the entries of row R of B. Okay, so this would be the same as that. Alright, so we separated this again. Of course. We separate. Stay hydrated, Delta. Oh yes, of course. Look. Are you Dinobot or something? Emperor Paradox is Dinobot. I have Dinobot in the stream. Okay, so Delta Arcade. No, what was this? This was a okay, this is in the matrix C, right? So KJ from okay, so K goes from R. Alright, so these are all the rows below. So wait, what was R prime? Yes, R prime was okay. Yeah. So of course, below R prime, yes, below R prime, everything is zero, of course. So everything here disappears. Now we have this, and so the matrix C, K, J. Now wait, now the deltas are the zero. Why? R, K. From 1 to R prime. Delta R, R. Is it because of this? What was the from 1 to R prime? So from delta R1 to delta R prime, they're all zero. And where were we? Here. Delta R1 to delta R prime, they are all zero, so this turns into zero, of course. So I'm following the proof, but this is new for me because you see, usually I just breeze through everything we see in class in math. So I just see it and understand it easily. But here, this is new for me because I'm following the proof, but I don't understand it intuitively. It's just so weird. This has never happened to me, I think. Well, at least I can follow the proof. So yeah, I'll just review it later. Probably not even in the stream, maybe some other day. But I need to get used to these absolutely brutal proofs. Okay, so row R is a totally zero row, contradicting that this should be. Wait. Oh, right. So it can't be a non-zero row. So this, and by a similar argument, okay, we have that. Let's combine the first three steps. We can see that D equals D prime. So B and C can have the same pivot columns in the same locations. Alright? And fourth step, okay, final step. I'm actually doing it. I'm surprised. In this final step, we will not argue by contradiction. Our intent is to determine the values of the delta ij. Let me guess, they are all 1. Notice that we can use the values of the di interchangeably for b and c. and it ends here. Okay. Step 4. Wait, where was it? Here we go. A whole page of sigmas. I love it. Here we go. 1 equals b, I di. Yes, easy. Okay, so from 1 to m. Okay, this is the same as that. Okay, so we take out the I, and what is 1, and all of the others are 0. Of course. Mm, yes, they're all 0. Okay. Yes, they're all 0. Okay, so this is equal to delta II. Delta II. So for all delta II, they're 1. Wait, what? So, wait, no. Oh, right. So, yes. I understand this. Finally, I think. So, like, the rows, like, this is. Okay, I made this absolutely massive. Okay. Let's make it like that. This is B. This is B, and this is C. And we have each row. Let's take this row, row I, row I, and this is row I to put in C. And we have the deltas, which are like the delta times C of I K. Was it I? No, K. What was it? I don't know, whatever. So you take the deltas of a, so you multiply them like this row using the row operations will go there, multiply by some delta, and so the delta I for the same column is 1. So this column is the same as this, but this one will have the other ones added by some delta, which I guess will be 0, of course. And sure enough, this proves that 0 is equal to the others, right? I guess, and from what I can see. So this is if, okay, so we have that this is, okay, so, and if L is not equal to I, so of course for every other row it's 0, so it's just the same rows. So B is equal to C because everything is the same. So 0 is equal to B I D L. Yes it is. It should be right. Yes. And the summation from 1 to m of delta ik times C KDL. C. Wait, how long has this stream been going? It's still going. Well, 3 hours. Okay, we are 1/6 of the way there. Alright, let's go 1/6 of the way, just for a proof. And like basic stuff that I knew. The difficulty just went from like 0 to 100. If there's anything more complex than this proof in this whole PDF, seriously, please, no. Seriously, I just went from speed reading everything, speed reading through stuff I already knew. To spending like what, an hour on this. I don't know how long I have been on this. Wait, where was this? Here. Okay. For L different to Y, to I, not Y. From L different for L different to I, we have this. Okay. So K D L. We separate this one. So for K equals L. And this will be equal to 1. And the others will be equal to 0. So we have this is equal to 0. So let's have B equals C for all i's, all j's, because B I sub j is equal to 1. Okay, this by definition is captain property. What's this? Oh, what? Okay, whatever. I don't think you need to specify that. Okay. Um. So you take this one out of the sigma, the summation. The other one will. Okay, this is all 0. No. No, I was here. Okay, so of course. So this is delta II, which is 1, and the others are all 0. So this disappears, and we have this. So they are the same. Bruh. 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 Was there not a simpler way to prove this? Seriously, was there not a simpler way to prove this? I'm sure there has to be. Okay, so B and C have equal values in every entry, and so are the same matrix. Thank God. Okay, so we will now run through some examples to solve systems of equations. All of this, I could have skipped this, okay? All of this is just to make sure that you can solve like 2x plus y equals 3, and then x minus y equals 0. Well, not really, but it's similar stuff. I mean, okay. You work on box and circle and write them in different colors, identify them. Are you kidding me? You just went from full formality, from like this, to using M. Okay, whatever. This device will prove very useful later and it's a very good habit to start developing right now. What? Using matrices to draw a common formula. We mark the living ones with a small box. Okay, okay, okay. Of course. Solutions for archetype B. Huh? I don't know what archetype B is. Okay, so we have this segmented matrix. After that, okay, so you switch these up. Then this is gone, this is gone. J equals 2. Okay, this is 1/5, this is gone. And same here, this is, wait. Alright, this, okay. So this is the reduced row echelon form, okay. Matrix of a very simple system of equations. Yes, it is. Which has an obvious solution, which is this. The only solution to the system. So we have determined the entire solution set. This. And that's it. Yes, it was worth reading that proof. Clearly worth it. You might compare this example with the procedure we used in example. Okay. They contrast each other in many aspects. I don't know what archetypes A and B are. It's somewhere in like page 500. I didn't read it, so. But yeah, it's okay. Let's solve archetype A for now. Or archetype A is this. No, okay. Solutions for archetype A. Augmented matrix. Okay. Double column form. Okay, reduced. Double column form. And wow, the third row is gone. A bit differently than for archetype B. Yeah, because this is now this row is useless. There's no restrictions on our possible solution, therefore we can safely ignore it as we analyze the other two equations. Which are these? Wait, where's okay. Therefore easy to solve as appears to have multiple solutions. An infinite amount of them. Wait just a moment, can I see this? Oh, what? Alright. Whatever. What's this? Nah, never mind. This is this much I can. I don't think I can do in 3D. No. Okay, never mind. Well, this system is so you should pick any value of x3 and figure out. Okay, yes, I know. So this behavior, we say that x3 is a free variable. Why x3? Because you can. The augmented is not a pivot column. So the equations solve each for the variable whose in it with. Notice that the third column of the augmented matrix is not a pivot column. Okay? It isn't. So, if it's not a pivot column, wait, well, the same as the column index of a pivot column. So yeah, you can just act as if this x3 is like some constant, and then change the constant. Okay. So to write a set of solution vectors in set notation, we have this. Of course, and then we have this, and the x3, which is actually constant, but it doesn't matter. Okay, so we'll learn more in the next section of systems with infinitely many solutions and how to express their solution sets. For now, you might look back at example IS. Okay. Wait, so Wait. Okay. Solutions for archetype E. I don't know what archetype E is. I have no idea. Let's find the solutions for the following system of equations. First, form the augmented matrix, this, okay. So echelon form, and wait, what? So this has no solutions. The equation will read 0 equals 1. So it's false, right? So that's it. Alright then. Notice that we could have reached this conclusion sooner after performing the error operation. Yeah, I didn't go through absolutely everything. Oh yeah, this. Right. You can see 0 equals -5. Statement. We're going to read the matrix of the way to reduce the echelon form as per this. These three examples illustrate the full range of possibilities for a system of linear equations. No solutions, one solution, or infinitely many solutions. In this section, we will examine these three scenarios more closely. We will often speak of row reducing as row reducing a matrix. This is an informal way of saying we begin with a matrix A and then analyze the matrix B that is row equivalent to A and introduce row echelon form. So the term row reduce is used as a verb but describes something a bit more complicated since we do not really change A. Okay, so yeah, you use row echelon form and that's it. Is a matrix from row echelon form? Yes. Use row operations? No. Well, maybe I could, I guess. But it's going to be a notepad. 2, 1, -8. -1, 1, -1, -2, 5, 4. Okay, this matrix. So well, let me put this here. Okay, so yes, I'll go ahead and no this. It's just be easier to do this and do this and then this, this and this. Okay. So now this is 0. This will be 3, and this will be -10. And if we add this here, 3, 6. Now this is going to be, well, I'd rather have this here, 6, like that. Now this is 1, this is 2. So this will become 0, and this will become 3. And this will become 0, and this will be -10. negative 16. Okay. And now this is supposed to become 1. This is just the unit matrix. This is just the unit matrix. Wait, really? I mean, it is possible. It is possible. So why not? I'm sure. Yeah, I'm sure these matrices that have Reversal reduction to the unit matrix will be special later. I'm sure about that. I mean, I don't know. It has to be. But well, this would be, I guess, the more normal result for square matrix at least. Because the other possibility would be like this, this, or this. So yeah. Okay, let's go. Final solutions to the system below. No thanks. So if I understand this easily, I think I can just skip it. So type below system. Form the augmented matrix, convert the matrix to reduced Echelon form, and describe the solution set of the original system of equations. I might do one. I might do one with solution as a set, using correct set notation. I might do one, but I'm not going to do one of these massive ones. I just do one of these simple ones. The big ones are the same, but like more time consuming. Right, so I'll move Notepad over here. And we have two variables. 2x plus y equals 6. Negative x minus y equals negative 2. And 3x plus 4y 4y is equal to 4. So okay. Wait, I should have just done this like in row echelon, I mean like this form already, but whatever. Negative 1, negative 1, negative 2, 3, 4, 4. So reducing this to row echelon form, I'll just change these positions and this. Now it's just 0. This would be negative 1, and this will be 2. This will be 0, 1, negative 2. Yeah. So about that, these are the same. So I can just remove one of these. There is one. It doesn't matter anymore. I mean, well, it's just all zero. So when I remove this, this will be 0, 4. Okay, so this is the final. This is the row echelon form. Okay, so that's fine. What now? What to do now? So this is 0 equals 0. Okay, so this is gone. So now we have y equals -2. Then we have x equals 4, so that's it. 8 minus 2, 6. -2 plus 2, -2. No, -4, I mean. And then 12 plus minus 8. 12 minus 8, 4. Exactly, it works. Yeah, it works fine. Okay, so wait. 4, -2, right? So the solution is, let me write this in fancy notation. The solution is 4, -2, right? 4, -2, the vector here, okay. So there goes the vector. I'm not doing any of these anymore. Reduce the matrix within the row operations. No thanks. Here's the 3 by 4 matrices below. So reduce each matrix and determine that the reduced row echelon forms of P and C are identical. From this, argue that P and C are row equivalent. Okay, I can do that. I'm not going to row reduce them, so I'll just assume that they have the same reduced row echelon form. So okay, according to that theorem, this, right, is reduced row echelon form is unique. I mean, yes, sure. If you have a matrix A and you have the reduced echelon matrices B and C, then they are the same, right? They are the reduced row echelon forms of A. They are the same. So, if you have another matrix, wait, this is A, this is B, this is C. Here we have matrix B and matrix C. So if B, the reduced row echelon form of both B and C, well, actually you don't need that. You don't need that theorem. But you have R, let's say it's R. Then from B you get to R by doing the equation operations. And same from C to R. So if B and R are row equivalent and so are C and R, then so are B and C. Okay. Oh look, more deltas and more. Oh my god. In the proof of theorem, remember when the entries of row equivalent matrices are related by way of certain scalars and sums. In this example, we would write that entries of B from row I from of B, well, okay, from row I that are in column J what? There's only one entry there. Are linearly related to the entries of C in column J for all three rows. Yes, okay, so okay, we're talking about these two matrices. Yes, so yes, this is right, yeah, I guess. the ij's delta, different delta for each column depends on these columns and on, no, on these rows and on these rows too. So yes, and the corresponding three scalars in the relationship. So your answer will be 9 scalars determined 3 at a time. No, no thanks. I don't want to. I mean, come on. Why? Is there even a way that isn't trying everything to solve that? There should be. Maybe with the row echelon form. There should be. So if you like turn B to row echelon and C to row echelon and then B to row echelon to C by reversing these steps from C to row echelon, then you get everything here. So like if you get all these steps from B to C, then I'm sure you can get all the scalars. Yes, I'm sure you can get all the scalars, but I'm not going to do that. It takes too long. I want to keep going with this. Okay, these are just extra. Prove that each of the three row operations is reversible. While switching them, you switch them back. Multiplying something by an alpha, just multiply by 1 over alpha. Now there's the other one. Okay, so you have row 1, well, row I, 1, and row I 2, and you have the new row I 2, so I call it row I 2 prime. This is some alpha. So how do you reverse this? Well, you reverse this by saying I prime prime 2 is equal to negative yes, like that. Okay. If different row equivalence to prove the following three facts. A is row equivalent to A. I mean, come on. Yes, yes they are. They are, of course. Wait. I mean, yes, of course. Wait, I got pinged. Why did I get pinged now? Oh, okay. I can't open that in stream. What is bridge streaming? Switch drawing. Bruh. Why would you watch a drawing stream when you have 18 hours of linear algebra? Um. Alright, so there's some mod stuff going on. Oh, never mind. It's for the admins. Bruh. Okay, whatever. Sure. Okay, where was I? Someone's getting bent today. Um, was here. No. Oh yes, here. Okay. Wait. So paint. What was paint? No, this. I don't need this. Where was paint? Here. Paint was here. And wait. I'll just do that. Okay. So this is it. Okay. If A is equivalent to B, then B is equivalent to A. Yes, you can reverse every change. If A is equivalent to B, B is yes, if you can go from A to B, and from B to C, you can do A to B to C. Yes, of course. I'm not saying it in like the most formal of ways, but I know. Um, a relationship that satisfies these three properties is known as an equivalence relation. Yes, yeah, like symmetry and transitivity or something. I think it was like some prepositional. No, I know. Whatever. Oh, behaves like equality. Yes, sure. Okay, so um, this. Yeah. So give any collection of k adjacent rows. Give columns 1 through L. What? So you're just leaving it like that? It's the same matrix or wait. Whatever. Any k rows. Wait. It's in reduced Rabel form, but then use K by L matrix C, giving any collection of K adjacent rows. So other rows, like I don't understand. So screw that. Let's keep going. Page 59. We will now be more careful in analyzing the reduced Rabel form derived from the augmented matrix of a system of linear equations. We see how to systematically handle the situation when we have infinitely many solutions to a system. We will prove that every system of linear equations has either 0, 1, or infinitely many. Is there going to be another super massive complex proof? Please now. Please. For the love of God. The computer scientist Donald Knuth says will I'll just read this silently. Consistent if it has one solution, otherwise it's inconsistent, okay? So we will want to first recognize when a system is inconsistent or consistent. This minus in the row echelon of matrix. Okay. Yusuf. Ah, wait. The minus in the reduced row echelon form of a matrix using the value of R and the sets of column indices D and F. Okay. So D and okay. Okay. Hmm. I'm sorry. Okay, so let's see. There's echelon form notation. We have this matrix in reduced row echelon form, and we have R equals 4. So there are 4 ones. So like 4 rows here. V equals 1. The 1 okay, so the pivot columns 1, 3, 4, 7. 1, 3, 4, 7, and the others are the F. So okay, we have the sets and R. Partition of the set of column indices will have nothing common. Well, of course, because B is the indices of the pivot columns, and F is the indices of the columns that aren't pivot columns. So, I mean, yeah, it makes sense. What do you expect? The number R is the single most important piece of information we can get from the reduced row echelon form of the matrix. It's the holy grail of the matrix. It is defined as the number of non-zero rows, but since each non-zero row has a leading 1, it is also the number of leading ones present. Um, For each leading one, we have a pivot column, so R is also the number of pivot columns. So R is everything. For different situations, each of these interpretations of the meaning of R will be useful. For now, pivot columns. Okay, so what do we need pivot columns for? Um, Alright, for principal theorems about the possibilities for solution sets to systems of equations. Let us analyze one particular system with an infinite solution set very carefully as an example. I use this technique frequently. Okay. Archetypes I and J. I don't know. Wait. Is there anyone here, by the way? There. Ooh. Oh yes, there are people. There's someone. Okay. Where was archetypes I and J are both fairly large for doing computations by hand. The properties are very similar, so we will frequently notice this situation in archetype I and if you the joy of analyzing archetype J yourself. Oh yes, of course. So we're representing one with archetype I with next. Okay, so let's do that. The archetypes is driving systems of equations. Usually is the value of RD and I. Okay. Okay, 4 equations in 7 variables. So this is the reduced Rowe-Echelon form. R equals 3, and well, we have set B and F. Wait. I note any one of the 3 non-zero rows. Then the index Pi is a pivot column. Yes. Yeah, the index Pi is a pivot column. It will be easy in this case to use the equation presented by row I to write an expression for the what? The variable vi, yes. So the variables, okay. Wait. Using expression for the variable vi. Wait, what do you mean? There's no x2 in row 2 or x3 in row 3. Oh, xdy, xdi, of course, yeah. Okay. In a function of the variables of the other variables. Okay, yes. Notice that using subscripts upon subscripts takes some getting used to. Well, okay, so for I equals 1, we have xd1, which is x1, x3, x4, and we get the constants and then the others. And that's how we do it, okay. cannot. Okay, okay. Wait. So, depend. Depend. Oh, all right. So we get one. So you get the dependent values, which are the x 2, 5, and 6, and 7. 2, 5, 6, 7. You can change those. And you express this as I said. It looks pretty. It looks pretty. Yeah. Yeah, it looks pretty. Not fun, I guess. The condition that x2, x5, x6, x7 specify the variables are free to assume any possible values in the complex numbers, of course, the complex set. Mm. Okay, I'm sorry. Will allow us to create a precise description of the solution set for any consistent system once we have found the reduced row echelon form of the augmented matrix. Perfect. We could program a computer to do it. Yes, you could. Now have a whack at archetype J. No, I won't. I won't in Paint. It's painful. Using the reduce row echelon. Wait 1 second. Oh, okay, there. Using the reduced row echelon form of the augmented matrix of the system equation. Very key idea. Ooh, the definition. Okay, so independent and dependent variables. Suppose A is the augmented matrix of a consistent system of linear equations and B is a row equivalent matrix in reduced row echelon form. So you mean the same matrix in reduced row echelon form? Suppose J is the index of a pivot column of B. Wait. Suppose J is the index of a pivot column of B. The variable x sub j is dependent. The variable that is not dependent is independent. Okay, fine. You might wonder what to do if the system has n variables and column n plus 1 is a pivot column. That's impossible, right? that's impossible because you have like this and like the ones will be all here in the diagonal. Could deviate a bit and go like here and here and here and here. But they can never like get here. Okay, so the system of 5 equations in 5 variables, and this is the um, row reduced echelon form, row echelon form. Okay, so wait, before looking at any of this, I will try to solve this. Well, I won't solve this, but I'll say the steps. Okay, so reduce this to row echelon form. Easy. Here it is. And now, okay, let's see. Now I see these are the dependent variables x1, 3, and 4, and the independent variables are 2 and 5, x2 and x5. So you move the x2 and x5 here to where the constants are, and well, that's it, basically. Yeah, that's basically it. And then you get like this, since everything here is 1, 1, 1, and all the other numbers are the independent variables, which are at the right side anyways. Then you can get, so x1 is this, whatever it is, x2 is 2, x4 is x4, x5 is x5. There are no 6 and 7 here, so this has nothing to do with it. And then there's 3 and 4, 3 and 4, which are dependent. Well, you just get this, like x3 is equal to 1 plus 2x5, and x4 is equal to 9 plus 4x5. Well, I actually solved it. It wasn't that bad, I guess. And x1 is equal to 6 plus x2 minus x5. No, minus 3x5, yeah. X5, x2, exactly this is, and of course this. Okay, that's easy. Okay, the solution says this. Fine. Notice how we spread the freedom for x2 and x5 here, yes. Sets are an important part of algebra. Yes, they are. I mean, isn't set theory like the foundation of most of modern math? Like, to get out of set theory, you have to, to get some absolutely brutal problem. Getting to the limits of absolutely everything. Like, not even set theory, just like to get out of the CFC theory with Sermelo-Frankel with action of choice. Just to get out of that, you have to get some absolutely insane stuff. So yeah, I guess that set theory, which is even bigger, because it's that and more. I assume that's even like much more even. Okay, we can now use the values of M and R and the independent and dependent variables to categorize the solution sets for linear systems to a sequence of theorems. The following sequence of proofs you will want to consult 3 plus techniques. There are more proofs. Boy oh boy, I sure hope there are no pages full of sigmas. No, there aren't. Fine. Okay, 63. What was it? Proof technique E, N, and CP. You know, I don't like how CP sounds. It could be Cloud Penguin. It could be Cheese Pizza. But, yeah. I don't like how CP sounds. When a theorem uses the phrase if and only if, it's a shorthand way of saying that two if then statements are true. So yeah, if P then Q and if Q then P. PP, fat boy. Hi there, PP. Yeah, I don't know, I think CP sounds worse. Yeah, let's forget it. So to that if Q then P. So I will wear bright yellow knee-high plastic boots if and only if it is raining. So of course, my boots. Okay. So if you get a theorem like that, of course, you get to prove stuff both ways. But you have to prove it the two both ways, yeah. Of course. Okay, so before we then prove with reminders in which statement is being used as the hypothesis. I wish I could write such carefully written proofs. My proofs in the Math Olympiad are fucking shit. Well, I mean, depends. If the problem is easy enough, I guess. But there's nothing even close to what I just saw there. Like all the sigmas and deltas, nothing even close. Should I need to read that? If I could make a proof like that, I would have won the Math Olympiad, like second phase. Okay, so a careful word and proof will remind the reader which statement is being used. Wait, by the way, I'll just mark that. And I also want to see how long I have been going at this because you see, I'm going to be here for 18 hours. So, YouTube only allows 12-hour long videos, and that means that at some point I'll have to end the stream and restart it so that I can upload so I can upload the whole stream. So when I'm around 9 hours, probably I'll end it and restart it. Yeah, somewhere around there should be fine. Okay, so anyway, where was I here? Basically half first, since I know until you have finished doing both halves. Oh well, if you rewrite your proofs, then choose to put the easy half first. Bruh. Yeah. Yeah, okay. In terms of this type of equivalences or characterizations, some of the most pleasing results in mathematics. Yeah, I guess. So it's correct. Proving P implies Q is very easy, then proving Q implies P is likely to be proportionately harder. You can prove that P is in MP. Well, you can't prove that MP is in P. I mean, you can, you probably can, but okay, what's this? What, what does this mean? What? Just multiplying numbers by about 3? Or what? What's this? What's next? 300,000? Wait, no, never mind. Oh yeah, probably. Okay, so wait. I wonder what this would say now. Okay, I see. Alright, so yeah, this is just if and only if proofs. Oh, look, I was right. What does this mean? I don't understand. Okay, so when okay, proof technique negation. When we construct the contrapositive of the theorem, proof technique CP, well, penguin, of course. Contrapositive. Contrapositive, isn't that like P implies Q? Yeah, if P implies Q, then like not Q implies not P. Yes, I think that's it. There was inverse, there was converse, and this was the contrapositive. I don't remember which one was the inverse and which one was the converse. I know they are the same anyway because one is the contrapositive of the other, but yeah. Let's negate two statements. Yeah, so if P implies Q, then not Q also implies P. No, not Q also implies not P. That's the contrapositive, right? If a statement says that the set is empty, then the negation is that the statement has the set is not non-empty. If a statement says something that happens for all I, for every I, or for any I, the negation is that something does not happen. Here's for at least one value of I. No. Oh yeah, these are the same. Yes. For at least one value of I, but not for like every. What's this? Are you in like the ordinal markup or and like clicking the like starting from 0 or what? I don't understand. What's this exponential growth? Check this out. Okay, wait. Here. Okay, I shouldn't be with ordinal markup, but I'll show it for a bit anyway. If it wants to load, of course. Wait, where was I? Here. Oh, there we go. Check this out. I'm trying to get this to 1024. Well, maybe I should buy this. Yeah, maybe I should buy this. I think, yeah, it's a good idea. So I'll get this, get the last manifold, get the last manifold for this, and get 19 manifolds. Well, not 19 singularity. That's pretty nice. What happens someday? Well, there's nothing here, so yeah. But when it happens, I'll make a video about it, I guess. What? Wait, what? What? Wasn't even past that. Past what? Like past this? I mean, I don't know. I just kept going. I don't think you're trash. I don't know how you can be trash at an idle game. Just I don't know. Just keep going. Like it just takes time. It's not that you're trash. It just takes a lot of time to get here. Didn't you like lose your progress? Then that's the reason why you're not here because you lost your progress, not because you're trash. All right. So I'll keep going with this and counting faster. Count up to like Graham's number if you can. By the time you have counted to Graham's number, I'll have finished this and like a PhD on linear algebra, if anything. What was this? Anyway, just okay. So where was I? Contrapositive. Contrapositive for an implication. Okay, not Q implies not P. This is the same, of course. Like according to proposition, I think it was not prepositional. Propositional logic. These are the same. Yes, this is a tautology. Uh-huh. Oh, it's true. Anonymous tautologies. Here it is. Just sprinkling some propositional logic in here. Well, this is linear algebra. For example, there's a theorem that if a vehicle is a fire truck, then it has with tires and has a siren. Yes. The contrapositive is if a vehicle does not have big tires or does not have a big siren, then it is not a fire truck. Yes. And then became the origin with the negation. Isn't that the Morgan's laws? The Morgan's laws? Yes, I think so. Will frequently happen. It's easier to construct a proof of the contrapositive than of the original implication. So then do it. Alright, where was I with this? In page. I need to save the page every time I get linked to something else, or else I won't like find it at some point. Okay, page 63. Wait, what's this? Ooh, okay, I see. Alright, yeah, that's a bit past Graham's number now. Yeah, that's quite a bit past Graham's number. This is like what, 505,000 errors? This is whatever I have there. Although this shouldn't be an exponent. It's more like it's a it's under like that. It transfinite ordinality. Yes, that's this. Well, this is a number, not a yeah, sure. What's the biggest number you know? Like of the ordinals? I know there's like model cardinals or something like that, but I don't know what that does. I know like up to the inaccessible cardinal a bit, just like just a little bit, and that's it. That's the most I understand. Yeah, VHO is like puny in comparison to that. The VHO is like in comparison to cardinals, VHO is a left null. Like the size of VHO in cardinals is left null, so it's nowhere near the inaccessible cardinal. We'll be back in an hour, okay? I'll still be here unless I'm having lunch. Yeah, I'll be eating probably in an hour, but it's okay. I'll still be here for 18 hours. Okay, so where was I here? Proof of the name CP. First, we have an important theorem that wait, wait. God damn it. Uh, anyway, uh, theorem recognizing consistency of a linear system. Okay. Suppose A is the augmented matrix of a system of linear equations with n variables. Suppose also that B is a row equivalent. Okay, anyway, we have A. Let's make it like that. With n variables. This row equivalent matrix in reduced row equivalent form. So the same matrix in reduced row equivalent form with R non-zero. We have R. And the system of equations is inconsistent if and only if column n plus 1 of B is a pivot column. What? If column n plus B is n plus 1. What? There are n variables. Okay. So it has to be more like elongated like this. Okay. It has to be elongated like this. And if this, so there are n variables. If anything, this is like this. It can't be, you can't have the n plus 1 being a pivot. Oh yes, sure. Yes, you can. Because the last one is the constants, the augmented matrix, of course. So if this is all zeros and this is a 1, then of course this is inconsistent. Right. So proof. The first half of the if and only if, by the way. So this is the easy part. Easy. The column n plus 1 of b is a pivot column. The leading one of row r is located in n plus 1, so okay. This represents zero equals 1. So yeah, that's it. Easy. Now we have this. So for the second half of the proof, we wish to show that if we assume the system is inconsistent, then column n plus 1 of b is a pivot column. Right. So proving this directly will form the logically equivalent statement that is the contrapositive. So if column n plus 1 of p is not a pivot column, then the system of equations is consistent. Alright, fine. This goes up to here. Okay, this should be simple. If column n plus 1 of p is not a pivot column, the leading 1 for row r is located somewhere in columns 1 through n. For the leading one for row r. Wait. The leading one for row r. What's that? R non-zero rows, okay. Okay, somewhere in columns 1 through n. And every preceding row leading one is also located in columns 1 through n. Yes. In other words, since the last leading one is not in the last column, no leading one for any row is in the last column. Yes? We'll now construct a solution to the system by setting each dependent variable to the entry of the final column in the row with the corresponding leading one, and setting each free variable to 0. That sentence is pretty vague, so let's be more precise. Using our notations for the sets D and F from the reduced row echelon form. Okay, so we have that x, okay, equal to is equal to wait m plus 1. Okay, I see. Okay, so for each one of those, okay, and if that of those are 0, okay, I see. And these values for the variables make the equations represented by the first r rows to be all true. Convince yourself of this. Yes, I know. I can imagine it, I guess. Greater than r if any are all 0 rows. That represent equation 0 equals 0. They're also all true. We have now identified one solution to all the system represented by P. And so yeah, it's consistent. Okay, fine. The beauty of this theorem being an equivalence is that we can unequivocally test to see if a system is consistent or inconsistent by looking at just a single entry of the reduced row echelon form. Alright, it's back. Alright, there are no problems anymore. Okay, fine. No problems here. So the reduced augmented matrix as n plus 1, yeah, of course. consistent system. N plus 1 is in D. Okay. Okay. The characterization of theorem RCLS. What was that? Who have the idea of like naming every theorem with these letters? Why? Seriously, why? We can. Well, maybe it's. I don't know. I've seen some PDFs where they are more like the. Wait, what was that? Seen PDFs where they are more like theorem 1.5. So yeah, it's not much worse than that really. It's about the same, I guess. Probably, I don't remember. The characterization of theorem RCLS, we can explore the relationships between R and N for a consistent system. We can distinguish between the case of a unique solution and infinite solutions. Okay. So where is it? The characterization. We can explore the relationship between R. Wait, what was this? RCA. Nice inconsistency. Yes, but this doesn't have anything to do with how many solutions it has. Oh, wait, no, never mind. Okay, recognize that these are the only two possibilities. Okay, fine. Consistent systems R and N. Suppose A is the augmented matrix of a consistent system of linear equations with n variables. Okay, 1 second. A is the augmented. So the consistent system of linear equations with n variables. Also B0 with R pivot columns. These are the zeros. Then R is less than or equal than n. If R is equal to n, then the system has a unique solution. Wait, what? If yes, I mean yeah, that makes sense. But let's see this. Implication. This shows that V has n plus 1 columns. There can be at most n plus 1 pivot columns. So if this is, then of course this is inconsistent. So R is less than or equal to n. This is saying then there are no free variables. Oh, right. So that's the like the more rigorous proof for that. The resolution is given by setting the n variables to the first n entries of column n plus 1. Yes, finally, I have found the rigorous proof for this. When r is less than n, we'll have n minus r greater than 0. So yeah. Alright. Okay. Chosen. By setting the chosen free variable different values, can create infinitely many solutions. So that's the reverse proof. Alright. The next theorem simply states the conclusion from the final paragraph. To say explicitly the number of free variables. What? Why? Free variables for consistent systems. Okay. Is the order of the solution set can be described with n minus r free variables. Proof. See the proof above. Okay. Then why? What did you make this then? Is this even like a theorem? Shouldn't it be like a corollary? Or, no, a lemma. I don't remember what was a lemma and what was a corollary. 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 Yeah, corollary. Wait. Wait. Okay. Never mind. Okay. Alright, so counting free variables for each archetype. What? A has n equals 3 and r equals 2. So there's one free variable. Okay. Uh-huh. There's one free variable unless it's inconsistent, of course. It can still be inconsistent even if it's like this. This is 0, 0, this is a 1. Doesn't matter. Like it can still be like this. Okay, so and3 and R3, so of course. Okay, so yeah, the examples have accomplished a lot so far. The rule has been the following theorem, which is now very simple to prove. Which one? I don't know what you're talking about. The proof is so simple that we ought to call it a corollary, but the result is important enough that it deserves to be called a theorem. Okay. C proof dynamic LC. Okay, what now? What do you have for me? Lemmas and corollaries. Okay, page 66 right away. Titles. Okay. Claims and no, claims can be conjectures. So yeah. Right there. It's not too interesting in its own right. It's important for proving other theorems. Yes. Okay. The corollary follows very easily from a theorem. Okay. So that was it. Alright, I remember now. So anyway, a system of linear equations has no solutions, a unique solution, or infinitely many solutions. Well, I mean, yes. System is inconsistent or consistent. System with no solutions. The remaining two possibilities guarantee one or So yes, there goes that. Okay, and now what? Wait, I'm on page 67. I want to know. Wait, no, I'm going to go to this. Where am I in the thing here? Okay, so I'm about to get to vectors. I'm about to go eat, by the way. So I think I'll leave it here for now and come back in half an hour. Well, when it's ready, of course. I'm not even here yet. Anyway, so that's 67, right? 67. So one more theorem to round out our set of tools for determining solution sets to systems of linear equations. Then consistent, more variables and equations. Infinite solutions. Suppose a consistent system of linear equations has m equations in m variables. If n is greater than m, then the system has infinitely many solutions. Okay, cool. To be it has m rows in total. And 0 rows is less than that or equal to m. So it's less, okay. And so n minus r is greater than 0. Okay, so a consistent system with three variables will have an infinite number of solutions. Okay. Notice that to use this theorem, we need only know that the system is consistent, together with the values of m and n. We do not necessarily have to compute the row equivalent, reduced row equivalent. Wait, what? Hi, Fluffy. What's up?
Oh my god, you have a voice?
Yes, I have a voice, yeah. What?
I was wondering if that was you talking or the stream.
Yes, it's me, it's me.
Oh my goodness.
I'm doing
I
18
finally get to
hours of
hear
linear
the.
algebra.
Oh my goodness. This is insane.
Yeah, I know.
I finally get to meet the man behind the slaughter. I don't know if people can hear me, so I won't say anything.
Anyway, so what do you think about linear algebra? It looks fun.
So you're doing AP what?
Huh? Linear algebra. I'm doing 18 hours of linear algebra.
Oh, okay.
Take this out. This is absolutely fucking retarded.
Hmm.
It took me so long to understand this.
Are you learning this for school?
No, I'm doing it for fun, I guess.
That's fair.
Yeah.
We're not on a live stream, are we? I'm a little shy.
Huh?
I said I'm a little shy. Are we on a live stream or something?
Yes. Well, there's like how many people? There's one person here watching, I guess.
Okay. Also, you're a little laggy on Discord.
It's probably my phone. I'm using my
Yeah, you
mic.
should
My
probably move
phone is
here.
the mic, so It's a little shitty.
Oh, that's probably why.
With an app like this. Anyway, so I don't know. I guess I'll continue with the linear algebra. What was to say? Damn it! Now everything is messed up.
I need to doing that. I'm gonna get back to this other server I was in. See you.
Why? Okay, so damn it, where is it? What was I even doing? It was paint. It was paint. Yes. Okay, so notice that the use steering we only know that the system is consistent. Wait. God damn it, Floppy, I messed up now. Notice. Okay, yes, I am here, I think. Notice that the user steering we only know that the system is consistent, together with the values of m and n. Okay, then I should necessarily have to compute the row equivalent reduced row echelon form matrix, even though we discussed such a matrix in the proof. Okay, so for example, this substitution. Okay, having been handed this solution, we have 1, 2, 3, 4. There are infinitely more, of course. We know that the system is consistent, yes, and we know there are 4 variables. All right, there are 4 variables, and 3 there are 4 variables and 3 rows. So there has to be infinitely many solutions. Alright. These theorems give us the procedures and the implications and allow to completely. Okay. Here's a broad outline of how we would instruct the computer to solve a system of linear equations. Okay, so represent the system of linear equations in an augmented matrix. Of course. Okay. Convert the matrix to a row equivalent matrix in reduced row echelon form. I once made a program in Kotlin without knowing any Kotlin. I just learned it like in the bus. It was yeah. It was very similar to C++. It's similar to Java, which is similar to C++ in syntax at least. So, or at least the basic stuff. So yeah, wasn't that hard to learn. And I made a program that had to do this to then get to the inverse matrix of a matrix. So yeah, I've done this. Well, and maybe not this exactly. I don't know. Let's see. The matrix to a row equivalent matrix in reduced row echelon form using the procedure from the proof of theorem that identify the location using. Wait, this. Oh yeah, this. That. Pretty similar. Yes. Okay. Oh, well, I didn't do this for like checking if it's consistent or not, just to make the inverse of the matrix. And so R equals N. This is unique. They can be read off directly from the entries in rows 1 through N of columns column N plus 1, yes. And if R is less than N, if only the set all the free variables to 0 and read off the dependent variable values from column N plus 1. If the solution, if the entire solution, okay, yes. You find a completion not big enough to hold, okay. So, well, you can have one solution. And if you want to check if it's consistent or not, you can just say yes, it is consistent. You need one solution. The whole makes it all sound a bit simpler than it really is, yes. In practice of operation simple division, that will introduce round of errors. There should be zero sometimes end up being very small non-zero entries. Or small entries lead to overflow errors when used as divisors. Iterative studies can be employed to minimize these sorts of errors. Okay. Numerical linear algebra. There's more. Oh my god. In this section, we have again a foolproof procedure for solving a system of linear equations, no matter how many equations or variables. We also have a handful of theorems that allow us to determine partial information about a solution set without actually constructing the whole set itself. So now, Nuth would be proud. Oh, okay. Yeah, I'm sure he knew about this. I don't think this was some extremely unknown stuff 50 years ago. I don't know however many years old Nuth is. How can we usually recognize? Okay, these are the questions before the vectors. So yeah, this is perfect timing. How can we easily recognize when a system of linear equations is inconsistent or not? Okay, so if in the reduced row echelon form, there is a this is a pivot column. This is inconsistent, and if it's not, then it's consistent. Suppose we have converted the augmented matrix of a system of equations into reduced row echelon form. How do we then identify the dependent and independent free variables? Okay, easy. So we have like this is pivot column and this and this. This is dependent, this is dependent, this is dependent, and the others are independent. That means you have to just set them all to 0 to get the solution. For example, like, or well, just like move them all to the right, to here, to this part here, to like make them. Yeah. So, what are the possible solution sets for a system of linear equations? What are the possible solution sets? I don't know. There are many possible solution sets. Well, there's one possible solution set for each one, but I don't know what you mean with this. Yeah, it shouldn't be. That's horrible. Okay, so what are the possible solution sets? I don't know what you mean with this. Anyway, okay, in this try the infinite solution set for archetype J. What? Solution sets? Nah. Well, this solution is correct. Oh, what? What? This? Okay. This for archetype J. This. Oh my fucking god. Wait. So, there are sample solutions. Okay, so there are sample solutions. But if one of these solutions is correct, okay, I'll assume. Based on this evidence, explain how you know this system of linear equations has infinitely many solutions. Okay, so where are the solutions? Who knows? Okay, who knows? Anyway, so how do you know this has an infinite amount of solutions? There are 6 rows and 9 variables, and it's consistent according to that. It said there are solutions, so it's consistent, and there are more variables than rows. So it has infinite solutions. Okay. Wait, why am I getting pinged everywhere? Alright, okay. Alright then. Let's keep going with this. Just up to like page 74. The details for archetype P. The values of R, D, and F. What are those? I don't know the values of R, D, and F. And the values of R, D, and F immediately following. Where? Where? I don't see it. I can't do this if I don't see this. Okay? Okay. Anyway, for exercises, say as much as possible about each system. Anyway, whatever. This is one, this is one, this is. Yes, this is one, one. Um, 0. 3, 1. 0 probably, right? Like it's in row 3. Yes, this is, no, this is 0. And this is 0 too. This, I don't know. Well, this should be, yeah, this should be 1. This, I don't know. I don't know. Right? I think you can't know that. I think. And this, I don't know either because, of course. F1. 1. F1. I don't know. Well, I wouldn't know if I could look at the matrix, of course, but I don't know. It's possible each system solution set. Okay. Which theorems are you are using? No, thanks. Consistent. Okay. One solution. An infinite amount of solutions. I don't know. It might not be consistent. So either zero or an infinite amount of them. Yes. Either zero or an infinite amount of them. A system with 12 equations and 35 variables. Either zero or an infinite amount of them, same. And 8 equations and 6 variables. The reduced Rebec-Echelon form of the augmented matrix has 7 pivot columns. So if it has 6 variables, there are 6 columns. So the 7th column has to be like the last one. That shouldn't be a pivot column. So it's inconsistent. Without doing any computations and without examining solutions as much as possible. No. That beats symmetrics in reduced Rebec-Echelon form. Okay, whatever. How many free variables would we discover? But an inconsistent system may have R greater than N. So, yes. So like here, that I'll see it again. This is the pivot column that shouldn't be a pivot column. So how many free variables would we discover? -1. If these are all pivot columns, then yes, you would discover -1 free variable. Suppose A is the augmented matrix. If R equals N plus 1 prove that the system, so yeah, all of those are, which are N plus 1, N are like in the matrix, the normal matrix. Then in the augmented part is the other one, so it's inconsistent. I don't know these values. Wait. This matrix is an echelon form that is equivalent to the augmented matrix of a system of equations with n equations in n variables. Am I getting pinged again? Oh, never mind. Although, well, maybe. Suppose that B is a matrix. Wait, I'm just going to remove the pins. This one. Okay, just wait for a moment. I'm doing something. Okay. Never mind. Okay, suppose that p symmetries in row echelon form. Okay. Wait, prove that what? Okay, for all, prove that they k is greater than or equal to k. Okay, yeah, that's easy. I want to prove that rigorously right now. Equal to 2. And 1 is okay. 1 is less than or equal to k, less than L, less than or equal to R. Okay, which one was k? What was k? Okay, is this. Okay, okay. What's L? Okay, never mind. L is nothing. I, wait, what? No. Wait, what's L? Whatever. Decay. This is 1. Right? This is 1. Decay the L. If L is greater than K. Uh, K and the L. Then it's over here. So it's, we don't know. Now L decay. L decay. I know. Could be anything. And L is greater than K. Greater than decay. Or less than decay, so we don't know. Now decay L. No, decay K. 0. Wait, no. K, decay. The decay, here K, that K could be um, if a V or an F. We don't know. Um, decay FL. Nothing. Suppose that the coefficient matrix of a consistent system of linear equations has two columns that are identical. Wait. Suppose that the coefficient matrix of a consistent system of linear equations has two columns that are identical. Coefficient, oh yes. Prove that the system has infinitely many solutions. Yeah, this has something to do with ranks. This is hard. Okay, so Okay, okay. I don't know. I don't know. So let's say you have consistent two columns are identical. So prove that the system has infinite. Okay, so this and two columns are identical. Then, well, I don't know. Oh, well, damn. Okay, so okay. I think when you reduce them all to when you reduce the matrix to Rebecca form, like this is going to leave a hole here. This is going to be zeros. Okay, let me explain this better. So let's say you move these here. It does not matter. You can move them here, like the columns too, because I mean, it really does not matter. The name of the variables doesn't matter. So if you move these here, these two are the same. So when you reduce to Rebecca form, you're going to make this a one, okay? Maybe you do it like this, okay? You reduce this to one, and then you subtract this. Let's say it's alpha. So this is a one. So you also subtract column one prime. I'll say it like that. Is equal to column two prime. Column two prime. Equal to column two minus alpha column one. And of course, you also know that this and this are the same, and this and this are the same. So if you divide this row, wait, I mean row. I meant 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 row. So like this. Yeah, perfect. Absolutely marvelous. So these are the same, but if this is a one, you have divided this by alpha here, which is this number, and you have also divided this number by alpha. But when you're subtracting this, you'll be subtracting this by alpha again. So you will be like subtracting alpha by alpha times one, so alpha make it zero, and this, which is whatever it is, a two, a one, two over alpha, which is equal to a two, two over alpha. So I'm multiplying this by alpha, this one by alpha, subtracting a2 to this, then it will be zero. So you will have zeros here, right? This two will be zero, so the next one will be here at most, and then here, and then here. And since this is a square matrix, because um, um, wait, no, it's not. But anyway, so you have zeros there, right? So wait a second. This actually doesn't wait. Oh yes, yes, yes. So if you get to the end, these are the zeros here, whatever. This is the end, and you'll get to the end, and there will be at least this. There will be at least this, like 0. So there will be one column of one row of zeros because this like okay. So how do you say this? D2 will be 3 at least. So dn will be at least n plus 1. So there can be uh they can this can't be um a a pivot column, at least if it's consistent. Then you have one row here that is all zeros. And then, well, you have at least one, but you have, well, maybe not at least one, but you guys, so there have to be more variables at the end. So if there were more, if it was like this, there were more equations, it's going to end like this, and then a bit like that, at least one more. And all these are zeros. If it was like this, then it was already, you already had an infinite amount, so it doesn't matter. So yeah, that's it, I guess. Yeah, that's not a very rigorous proof. Consider the system of linear equations. Okay. Suppose that every element of the vector of constants B is a common multiple of the corresponding element of a certain column of A. Where there's a complex number alpha and a column index j such that Vi equals alpha times A ij for all I. Prove that the system is consistent. Wow. Well, that's why. Okay, what? What the hell is this? No, seriously, what the fuck is it? Um, select all. God. Okay. Consider the system. Well, I don't know. Well, I have no idea. Prove that the system is consistent. If the system is consistent, then the reduced row echelon form. Oops. The reduced row echelon form can have a pivot column here in the last one. Alright, so how do we connect that? What if there was? So maybe just a proof by contradiction, I don't know. Like I can't do that, now I have to go eat, so yeah. I'll be right back. Let's just do this and this. Let me edit this one second. How do I do this? I'm not sure. Oh, yeah, never mind. Alright, so I'm back. Where was it? Okay, here. Mm-hmm. There. Alright, so I have mentions here that I didn't see. Yeah, high quality stream. Uh, okay, yeah. Alright, so let's go back to mute chat and let's see what's here. Alright, so everything is fine. Uh-huh. Um. hmm. Okay, so what's up with this? There's one viewer. Who's that? Or is that me? Well, I mean, nah, it's probably me. Yeah, it's probably me. So, so back to what I was doing. I'm not going to prove this. And I'm going to go to this, the final part before vector. It was just the introduction, right? Okay, let's see. Well, yeah, I guess it was. Yeah. So now, in this section we specialize the system of linear equations where every equation has zero as its constant term. Along the way we will begin to express more and more ideas in the language of matrices and begin to move away from writing a full systems of equations. Hmm. So we'll begin with the definition. Okay, so homogeneous system. Linear equation zero vectors. Okay, and this essay. Archetype C is as a homogeneous system. So okay, this is an archetype C matrix. Well, system. Apparently, I don't know the archetypes. They're all found there in page 590. For each archetype, there is a system of equations. We have formulated similar yet different homogeneous system of equations by replacing each equation's constant term with a zero. Okay. For archetype C, we can convert the original system of equations into the homogeneous system that. Can you quite quickly find a solution to this system without reducing the augmented matrix? Well, setting everything to zero. So if x1 is 0, x2 is 0, x3 is 0, and x4 is 0, then everything is 0. You might have discovered those oh yes. The following theorems, so they are always consistent, yes. Okay, fine. So proof, set each variable to 0, yeah. consistent, consistent. Okay, fine. So they're consistent. Well, this trivial solution to homogeneous system of equations. What is the trivial solution? All x's are zero. Here are here are three typical examples which we will wait. Okay, so solution x1 equals 0, x2 equals 0, to xn equals 0. So x equals 0. Okay. The trivial solution. Here are three typical examples. Okay. Okay, so yeah, archetype B. Okay, so this. The augmented matrix row reduces to no, reduces to this. So all of them are 1. No, all of them are 0. Yes, all of them are 0. Alright then. Wait a moment. Wait. Does this mean that... Oh my god. Wait, so when they're square, when r is equal to the when there are as many equations as variables, does that mean there's only this? No, 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 right? Oh no, never mind. Yeah, no, yeah, forget it. Homogeneous infinite solutions. Okay, so homogeneous. What? What's that? What do you mean? Oh, wait, what's this? Homogeneous system. What do you mean homogeneous system? Right, that looked complicated. Homogeneous. Oh, all right. Sorry, I'm retarded. Um, Homogeneous infinite solutions. Okay, so this and this is to this. Okay, yeah. So exactly. Mm-hmm. Okay, so this reduces to that. So okay, it's consistent. So there are an infinite amount of solutions to with yeah, two free variables. All right, so there's that, and one. Oops. Um. What? Okay, so Okay, it's two free variables. Describe the solution set using the free variables x3 and x4. Exactly. After working through these examples, you might perform the same computations for the slightly larger example, archetype J. Yeah, I think not. I mean, I can, but I won't. That's for sure. Where was I? Archetype J, where's the archetype J? Here it is. Okay, so, oh wait, this isn't, oh right. This isn't page 674 here. That's what, okay, so, never mind. After working through these examples, you might perform the same computation. Yeah. Notice that when we do row operations on the augmented that's complementary zeros. Also real zeros, yes. Exactly. So what? Okay. Mm-hmm. What about this theorem? Homogeneous, more variable than equations, infinite solutions. Okay. Uh, So okay, it's consistent, and this, okay, yes. Well, alright then. Okay, so no space for matrix. So finally, this. Instead of solutions to a homogeneous system is of enough interest to warrant its own name. And it's a property of the coefficient matrix, not a property of some systems of equations. No spaces of a matrix. Okay, the set of all vectors that are solutions to the homogeneous system LSA0. Oh, okay. That's the null space. And what does that do? So I've seen it like numbers. The archetypes. Each example is a corresponding homogeneous system of equations listed, and several sample solutions are given. The solution will be elements of the null space of the coefficient matrix. Hmm? Alright, for example, this. Okay, so the write-off for archetype I. Okay, but this isn't. um, so the null space of a matrix. The null, okay, so okay, so the definition of the solve this homogeneous system that we remove this. Variables. So by the way, how long has this been here? 6 hours. Okay, fine. Well, the infinite solution set of sets using column vectors. Mhm. Yes. So this is what we have been doing, but um, yeah, never mind. Whatever. No space of this. Right. So the null space is okay. Yeah. Never mind. Yeah. So we got this. There are no free variables. So it's only this. Okay. Which always drop the solution set for a homogeneous system of equations. Um, there's always at least the zero vector. Suppose a homogeneous system of equation has 13 variables and 8 equations. How many solutions will it have and why? An infinite amount of them because it is consistent, and well, since it has more variables than equations, then yeah, it has an infinite amount of them. Describe using only words um, the null space of a matrix. Okay, the null space of a matrix is the set of is a solution set of a matrix. Wait, no, wait, no. The null space of a matrix is how do you explain that in like terms of matrices? Okay, so okay, what about I don't know. What about yeah, well, I know what it is. So it's like how do you explain it? With you just remove the last column, get all the zeros, like find the solution set for its corresponding system of equations. Yeah. Each archetype is a system of equations has a corresponding combinations. No. The key and all are just matrices. But then all space is the same. Okay. Compute the null space of the matrix. This. I'll do one of these. I don't care. Uh, let's do this. So we have. That's very big. So I'll do the second one. -6. No. Wait. Why there? I can do it here. -6, 4, -36, 6. 2, -1, 10, -1, -3, 2, -18, and 3. So this is 0, this is 0, this zero. Okay, so let's see how do I do this. So making it like decimals. Are you kidding me? I can't. Oh. Yeah, whatever. So okay. This is 6, and this is 4 versus 2/3. 2/3. What the fuck? Uh, okay, whatever. This is now 0. Yeah, 0. And this will be negative 7/3. Oh, and this. Yeah, this. -2. This will be 0. Will be this sometimes 3. So 4, and this will be 0. Oh, check this out. So I think I'll just, you know, got this, move this here. Now this is 1. And now this is just 0, just like that. There. Like that. And this is so the null space of this is just that. Alright, so the null space of this is just 0, 0, 0, 0, 0, 0. That's the null space. Okay, so without doing any computations and without examining any solutions, say as much as possible about the form of the solution set for corresponding. There's an equation that's basic stuff. A system of linear equations is homogeneous if and only if the system has the zero vector as a solution. If and only if, okay. It's easy to prove that. If it is homogeneous, it has the zero vector, but if it has the zero vector, is it homogeneous? If it has the zero vector as a solution, if it has a zero vector as a solution, then it will become like 0, 0, 0, 0, 0, 0, etc. equals equals. So what does it have? What does it have to be here to make it so that it's all correct? Well, of course, it has to be all zero. So yes. Yes. If it has the zero vector solution, it's homogeneous, and vice versa, of course. Mm, versus terms homogeneous. Um, I'm going to look at those theorems now. Suppose that you put that one solution with that V just a solution to what? To this? So okay, equations A, 0. Okay, so you have A, 0. Suppose that this is a solution. Okay, okay. So if this is a solution, that means that, where's the cursor? Okay, there. We have a 1, 1. I'm going to do this in paint. We have a 1, 1 u1 plus a 1, 2 u2 etc. all of that equals 0 and same here. So if you multiply this by 4, this is by 4, this is by 4, it's like multiplying everything by 4. So in the end, it's still 0, right? Okay, so this. Non-singular matrices. This section will specialize further and consider matrices with equal numbers of rows and columns, which when considered as coefficient matrices lead to systems with equal numbers of equations and variables. We will then see in the second half of the course, whatever that is, that these matrices are especially important. Oops. So square matrices. Okay, so be careful in your reading, writing, speaking. Okay, but wait. Alright, another proof technique, quote unquote. Alright, I'll try to read this quickly. Why didn't I already read this way earlier in the stream? I think I did. Yes, I did. I did. Just read this again. Nah. Okay, so this section. Okay. Where was I then? Yeah, here. This is within rooms and this is square of size n. Non-singular matrix. Okay, what's this? Okay, so if if a homogeneous system of equation, no wait. Okay. Okay. So you have a matrix. You have a matrix, and you do the system of equations. So it's all zeros here, the homogeneous system of equations. Then it's non-singular if yeah, perfect. Perfect. It's absolutely perfect. Brilliant. Otherwise, we say A is a singular matrix. Okay, so and what's this useful for? Okay, so it only works for square matrices, not for rectangular matrices or systems of equations, only for square matrices. Alright then. Wait, but why? Oh, well, never mind. Who cares? A singular matrix. Archetype A. Non-trivial solutions. Okay. There are. Well, then. Yeah, I'm not going to see them. This one is non-singular. Identity matrix. Oh yeah, there's one. The concept pivot column. Yeah, the possible pivot column appears once. This is the unit matrix. All right, just the diagonal. That's one. Non-singular matrices are reduced to the identity matrix. Yes, that makes sense. But a theorem. Okay, let's see it here. Okay, so A is a square matrix, and B is row equivalent. Row echelon form. Okay. So A is non-singular if and only if B is the identity matrix. Okay. B is identity matrix and the augmented matrix. So reduce. So this V, which is this. Okay. And 0 is equal to the number of variables. Equals R. And then there are no free variables. Perfect. And if A is non-singular, that's gonna zero variables, zero free variables. Well, then private columns, the permit to be the n by n identity matrix. Yes. Okay, so yes, well that's it. And this non-singular and has, well, the reduced echelon form as the identity matrix, so it works. Wait, yeah, sure. Okay, it works. Okay, but now what? So yeah, it's a non-singular. Okay, so now what? Null space of a non-singular matrix. Well, it's just the zero vector, right? And it should be. Okay, so here the null space is this. Okay, and this is a no, this is a singular matrix, and here it's non-singular and has one element. Just this. So okay, if uh, if A is non-singular, then null space only contains the zero vector. Yes. Well, okay, proof. Null space is equal to the solutions. Yeah. So of course. The next theorem pulls all big ideas together. Oh boy. Oh please no. Well, it doesn't look that bad. It's just that, just this. I mean, it's at least it's not like 3 pages full of sigma. So, theorem NMUS: non-singular matrices and unique solutions. Suppose that A is a square matrix. A is a non-singular matrix if and only if the system LS AB has a unique solution for every choice of the constant vector B. What let me read that again. Um, wait, wait, really? No way. A is non-singular if and only if system A B has a unique solution for every choice of the constant vector B. Whoa, that's very strong though. It's like a lot of conclusions. Like there's only one solution. It's for every B. There's a solution. It's only one. Whoa, that's that's very impressive. Um, so let's go. Hypothesis. So let's see. The system has a unique solution for every choice of the constant vector B. Okay, for v equals 0. The next solution is the definition of what it means for it to be non-singular. Well, wait, what? Wait, what? Make a very specific choice for v equals 0. Wait, what? Wait. But you're only putting it for 0. I don't understand. So if you choose 0, yes, of course. You got the solution, but where are the others? Yeah, anyway, I'll just read the rest. We know that A is non-singular of size n by n. So we know this is, wait. Yeah. Where A into the identity matrix I sub n. Mm. So, A prime will be B prime, which is I sub n C. So equivalent are equal n. And B prime represents the system of equations. Okay. Okay, so the solution so the system is consistent. The system is solution is unique. Yes, but so the solution is unique. Wait. Okay, so if it's non-singular, what am I doing? If it's non-singular, if it's non-singular, there's only one solution. Okay, so we have 0, 0. And then we have this. We have the, okay, so this is S. This is S. Okay, this is S. And, the first part of the proof. Okay, so you're saying that if you have any number in the end, a number here, in a non-singular matrix, you have anything here, it will work. Just like that, it will work. I'm not so sure about that. No, I mean, you didn't prove this here. It has a unique solution for every choice of the constant person. There's theory. So, yes, but you only chose one B. It's zero. Yeah, I don't understand. Whatever. Interesting. Non-singular matrices. So there's non-singular, no matter what the vector of constants we pair with, the matrix of the coefficient matrix will always yield a linear system of equations. No way. Will always, yes, with the solution. The solution is unique. Mm-hmm. Okay, so to determine if a matrix has this property, it's enough to just solve one linear system, the homogeneous system with a matrix as coefficient matrix, and the zero vector as the vector of constants. Okay. Formulating the negation of the second part of this theorem is a good exercise. Mm. Singular matrix has the property that for some value of the vector b, the system as AB should have. Wait, what? Oh, yes. Does not have a unique solution. It has no solution. More of this case later. Okay, okay. We'll be able to say more later. Square matrices that are non-singular have long lists of interesting properties, which we will start to catalog in the following recurring theorem. Mm, of course, singular matrices will then have all of the opposite properties. From the theorem is a list of equivalences. Okay, what's this? Understanding of what is involved with understanding and proving a theorem that has. Okay, so special form, specialized form of theorem, the following are equivalent. Hmm. All right then. All right. All right. All right then. Yeah, that's pretty powerful. Okay, so let's go. Where is it? It's lower, lower. Yeah, we're here. Okay, non-singular matrix equivalences. Round one. What? Suppose that A is a square matrix. The following are equivalent. A is non-singular. A row reduces to the identity matrix. The null space of A contains only a zero vector. And the linear system S has a unique solution for every possible choice of B. Alright. Prove the statement each of the subsequent statements in turn, well, those theorems. So the statement of this theorem is just a convenient way to organize all these results. Finally, you may have wondered why we refer to a matrix as non-singular when it creates a system of, equations with single solutions. Yes. So I wonder the same thing. We'll have an opportunity to address this when we get to theorem SMCD. Can you wait that long? 85. Oh well, probably not. Not today, definitely, that's for sure. Yeah, at this rate, I'm not going to get anywhere near close to that. Look at this. 7 hours. Well, no, almost 7 hours. So yeah, that. Um. Okay. Questions now. In your own words, state the definition of a non-singular matrix. Well, it's a matrix that only has the zero vector as in its solution set. What is the easiest way to recognize if a square matrix is non-singular or not? Um, Solving it like, well, solving it like, hmm, wait, no, wait, a bit far. Um, okay, this, and now we have this. So this is square matrix. Well, solve this, just solve this system, I guess. Yeah. If it has one solution, well, no, you don't even need to solve it. You just need to do the row echelon form. And if it's the identity matrix, then that's fine. Then that's non-singular. Yeah, like this. A row reducer. Yeah, you don't even know. You didn't even need the other thing. The null speed of it. Yeah, it's basically that. What is the easiest way to recognize is if a square matrix is non-singular or not? No, well, that's what I just said. Suppose we have a system of equations and its coefficient matrix is non-singular. What can you say about the solution set for this system? Say about the solution set for this system. It has one solution because it's non-singular, and by this theorem, well, this is equivalent to this. So yes, that's one solution. In exercises, determine if the matrix non-singular or singular. Well, I would have to reduce them to reduce the echelon form, and I don't want to, so yeah, screw that. So the archetype, find the null space for the matrix E. How do you do that? Okay, you get all zeros here and find the solution. That's it. Let A be the coefficient matrix of the systems. The coefficient below. Say non-singular or singular. Well, I don't know. For exercises, this. What is possible about each system's solution set? Be sure to make it clear which theorems you are using to reach your conclusions. Okay. 6 equations in 6 variables. Singular coefficient matrix. equations. Wait, singular coefficient matrix. 6 equations, 6 variables. Wait, this isn't square. This is basically it. Each system solution set. And there's something here, we don't know what it is. If it's singular, then it doesn't need to have a unique solution. System with a non-singular coefficient matrix not homogeneous. Still one solution, one single solution. 6 equations with 6 variables. Singular coefficient matrix. So it has more than one solution when it's all zeros. So there's not one solution, not one single solution. So it could, okay, so wait, the negation of this theorem, okay, so let's see, let me, linear system, the negation of this implies negation of this, okay. They are equivalent, so their negations are also equivalent. So if A is singular, then the linear system has a unique solution for every possible choice of B. The negation of this is doesn't have a unique solution for some choice of B. Okay, so that's the negation, so you can't know for sure. The fact that the stream is still going. Yes. 18 hours. I know. I said 18 hours. I'm going to do 18 hours. Alright, so hopefully get to like page 200 maybe. I don't know. Okay, so Andika. Okay. Are you from Quartz server? I think you are. Yeah, you probably are. So suppose we have a system of equations and its coefficient. Oh, so you are. That profile could. Are you Chunikyo? Yeah, Chunikyo, I think. Let me just. Wait. There's no Chunikyo. What happened here? Never mind. Oh, so you are. Then why can't I find Chunikyo? What happened here? What's going on here? Where did you go? Oh, well, I don't know what's up with that. Mhm. Oh, you're back. Hello. Okay, where was I? With paint. Okay, here. So, in exercise, no, where was I? Suppose we have a system of equations. So, no, wait, I was here. Yeah, here. So here I can say, and here I can say that um, system with non-singular coefficient matrix, non-homogeneous, it has one unique solution for being. Oh wait, no. Oh yeah, yeah. For being non-singular, even if it's not homogeneous. Now suppose I square. I think I see a pattern, and I think the C questions, the C exercises, are like computing matrices and computing stuff. M, I'm not sure, and P seems to be like the hardest, like the proofs, like the actual hard stuff. Mm-hmm. Well, let me get a bit like in a different position. Okay. Oh, I see. Smog quartz. Smog quartz. There you are. Oh, so you're Nikyo, not Chuni. What happened there? Uh, yeah. Ooh. All right. So, what was the T10? Suppose that A is a square matrix and B is a matrix in reduced row echelon form. That is row equivalent to A. Prove that if A is singular, then the last row of B is a zero row. Square matrix. Square matrix. A. Square matrix A. And square matrix B. And this. Okay. We have this here. So here it's all zeros. Okay, so A is a square matrix which reduced row echelon form. The last row of B is a zero row. Oh, the last row, not column. The last row. So if it's singular, there was another theorem back there. So if it's singular, if it's singular, if it's singular, does it need to be consistent or not? No, not really. Not really. No. Okay. Let me make a. No. This is a zero row. This. Okay. Fine. We have stuff here. This is singular. So if you have a zero column, you have a zero column, then wait no, it's singular. Well, if it's non-singular, then if you do the row echelon reduction, this is the unit matrix. If you don't, no wait, if it's not non-singular, so if it's singular, it can't be the unit matrix. So it either has greater R or lower. It can't be greater because, of course, it can't get out of the matrix. So it has to be lower, so there has to be at least one zero row. So yeah, I guess that was simpler than I thought. Using this, A is a square matrix in reduced form where it's algebra hard. Algebra hard, well, depends. It depends. Algebra. This isn't algebra like school algebra. So there are many algebras. Okay, there's the normal algebra you learn in school, which is just a bit more complex than arithmetic. It can be harder, of course. It can be much harder, I'm sure. This is linear algebra, which is, I guess, simpler. Well, it has more limitations. You can't do x squared, for example, or have trigonometry, but it still gets pretty complex. As you can see, this PDF has 646 pages, and it's a first course in linear algebra. So yeah, this is probably like 1 year in university, maybe, I don't know, of linear algebra. I'm not sure. I'm just guessing. But I know that this isn't just that algebra. This is, well, it's different. Just normal algebra, I think, in school it's pretty simple. But for linear algebra, at least at this level, which I think is just the most basic level for now, it's still pretty complicated. Did you see that? I mean, I have to read this proof. I have to read this. I mean, this took me like half an hour or more, so that was pretty complicated. This isn't really that complicated if you mm, learn all the theorems, I guess. So I say it's not that hard for now, except for this. It was ridiculous. So well, okay. Uh, well, there are some of these exercises that are about proving stuff. Those might be harder, especially in like the later pages. So I'm not sure yet. For now, it hasn't been that hard. Okay, so I was no, I was here. These definitions. Well, I should probably just click them, but it's really fun. It's really where square matrix reduce row echelon form where every column is a pivot column if and only if A is the identity matrix. A is a square. Uh, okay, I don't. Okay, page 86. Which one is this? This and this. Entity matrix, yeah. Hmm. Well, mm, I mean, it's pretty obvious, but I guess I could do it. Okay, let's go. Okay, using these. Okay, look, I don't remember what exactly was said there, so I'll just. Okay, it's a square matrix. If every column is a pivot column, it's a square matrix. So this is n by n. Okay, n by n matrix. Then, well, all of these are pivot columns. All of these n columns. Each one has a 1. And the number of pivot columns is the same as the number of non-zero rows. So there are n non-zero rows, which is all of these. And also, each non-zero row has a leftmost one, which also can't be less than a previous leftmost one. So it will go like this, 1, 1, 1, all the way here. Kusa, grass. Or do you mean lol? Because when math. Yeah, I'm laughing a lot too with math. I mean, as you can see, this is epic. It's absolutely so funny. This this stream is amazing, bro. It's going to get like 10 million views. 18 hours of math, of university level math, by the way. So it's not like adding 10 by 10 and 10. Okay, so all of these, this one has to be a 1, this one has to be a 1, all of these up the way to the end and the bottom. If all of these are 1s, then these are all 0s, these are all 0s. So of course this is the unit matrix. Alright, let's see what else is there. More exercises. What's the matrix B? Prove that B is non-singular. Okay, so if by doing equation operations, you could make a non-singular matrix into a singular matrix, or a singular matrix into a non-singular matrix, then you would be able to change their null space. If you change their null space, that means that here you have zeros. Okay, 0. All the zeros. This means that you have the system of equations and have a set S. And by changing it, you are changing it from singular to non-singular, or non-singular to singular. So you are changing the, well, so you are changing the null space. You're changing the null space, which is the solution set for one system of equations. By doing the equation operations, which can't happen, that's if that could happen, then you could change. And then the system of equation, the systems wouldn't be the same. So equation operations would be useless and wouldn't work. It has been proven that they work, of course. Suppose that A is a square matrix of size m by n. And we know there's a single vector B. There's a single vector B. The complex numbers. Wait, what? How is a vector a complex number? You're comparing vectors to scalars. What's this? Oh, wait. Suppose that A is a square matrix of size m by n. Okay. We know there's a single vector B. There's one vector. Such that the system has a unique solution. Do you mean that every single one of these numbers is a complex number, or because otherwise it doesn't make sense? That is a non-singular matrix. What? When there's a single vector B, there's a single vector, Then it is in non-singular matrix. Because in non-singular matrix, we have this property for every vector. So no, this I don't see how you want me to prove this. And yeah, I'll just go to vectors already. Okay, vectors. Okay, part 2, chapter V. You could say chapter 2, but now it looks like chapter 5, even though it's chapter V, not chapter 5. I mean, this guy really hates to use numbers. He really hates using numbers, seriously. So this is chapter 1, this is chapter 2. No, this is chapter SLE. And normally the theorems and dilemmas and the corollaries are 1 point something, but no, here CVSM. Come on. I mean, that I could see why, I guess, but this chapter V. I mean, so what's this chapter 5? I know that's just pretty weird. It's not like a big problem, but just really weird. Okay, I've worked extensively in the last chapter with matrices and with vectors. With place of vectors, while preparing to study vector spaces. Chapter VS. Mm-hmm. Chapter versus. This is where you fight the final laws of math. Okay. Initially, we'll depart from our study of systems of linear equations by section LC. What is LC? We'll first the connection between linear combination systems of linear equations. Theorem SLC. Oh yes, of course. Naturally. Wait, why? This guy Rajikari no sé qué why? Wait. Where? Where are you? Where did I get this comment? Oh, this, yeah. Okay, sorry. Okay, let's. Alright, let's go back to this. What's this? What's this? Ooh, what's this? This connection will not understand system of linear equations at a higher level. Oh yes, finally. I went to thinking like 7 dimensions. Well, actually, yes. Actually, maybe. Actually, yeah. Well, not 7 dimensions, but any number of dimensions. I think that's where it gets. And that's going to be pretty cool. I will finally be able to say I can solve systems of equations in a million dimensions. Well, not a million, but I'm not going to reduce a 1 million by 1 million matrix. I could program it, but I'm not going to do it myself by hand. This connection will allow us to understand systems of linear equations at a higher level, while consequently discussing them less frequently. Okay. So yeah, we're getting rid of the linear part in linear algebra. This is linear algebra, but we don't care about linear equations anymore. It's like, yeah, we need linear algebra for linear equations. And then eventually linear algebra just doesn't care about linear equations. Okay, fine. Hmm. Section below, vector operations. Oh no, here comes the multiplication. Probably. Okay. In this section, we define some new operations involving vectors and collect some basic properties of these operations. Well, by the way, I've watched this video from 3 Blue 1 Brown. Well, a few videos about the essence of linear algebra. And these vectors, even though it's just like 1, 2, 3, something like this, okay? It's just a matrix, really. They do have something, the vectors you learn in like physics and that, like this. So we have x, y, z, and more. So it's like the x coordinate, the z coordinate, and it's not necessarily that, but it could be interpreted as that, and that's why it's called vector. And it was stuff to do with linear algebra, so go check out 3 Brown if you are at this point of in the video and have no idea why vectors are called vectors because they aren't arrows. Well, they kind of are. You can define them for like 5,000 dimensions like this without drawing 5,000 dimensions in paper, which I don't know how you would do that. You can do 5,000 ones. That's like one in every 1,000 dimensions, just like that. So yeah, that's pretty cool. Okay, let me. Okay, let's go. You know, I'm not used to talking this much. I barely ever talk in real life. So, yeah, I'm not very talkative. So, talking for 18 hours now, it's going to be a bit of a pain, but it's okay. This section we define some new operations involving vectors. Well, before we continue, one more thing. How long has it been? Okay, so at 9 hours, I'm going to end the stream and restart it, okay? So it can be uploaded to YouTube because if it gets past 12 hours, it can't. And I want to make it like half and half. All right, that's all. Now let's go. The collection of all possible vectors of fixed size is a commonly used set. So we start with its definition. Of all possible vectors, ooh, that's a lot of vectors. That's exactly like one vectors. Well, not really. Well, maybe not. But 2 to the left 0, that's for sure. The vector space C M. So where basically this is like our this is the Cartesian product of complex planes. You have the complex plane. If you want to add a second one, you need 4 dimensions. You can't even draw the second one. Ooh, that's pretty. Ooh. All right, so let's see. The space complex. It's a set of all column vectors of size m. Oh, of size m. Yeah, of course. Yeah. You have m. You have 2. You have 2. And of course, you need one complex plane for this and another complex plane for dimension for that. Of course, makes sense. Of size m with entries from the set of complex number c. When I set is similar to this, when I set is similar So this is defined, what's this grammar here? We say similar to this is defined using only column vector. What? Okay, so there's a similar set which is R to the end instead of C. So it's the Euclidean space. So now we can have three R's there. Make like the vector here. This could be like what could this be? X is 1 and let's say y is, yeah, about 1 too. And C, I think this is the positive, this is negative, I'm not sure. Probably 1 too, I don't know. But like the real numbers, not like complex numbers. The term vector is used in a variety of different ways. We have defined it as an ordered list written vertically. It could simply be an ordered list of numbers, and perhaps written as that, yes. Could be interpreted as a point in n dimensions, yes, like that. Representing a point in 3 dimensions relative to x, y, and z axis. Referring to this one, exactly. Not like all of them. Just that one as an example. The interpretation as a point, we can construct an arrow from the origin to the point which is consistent with the notion that a vector has direction and magnitude. Wait. Arrow from the origin to the point, yes. So that's like the typical thing you call vector in physics. All of these ideas can be shown to be related and equivalent, so keep that in mind as you connect the ideas of this course with ideas from other disciplines. For now, we'll stick with the idea that a vector is just a list of numbers in some particular order. So yes, in physics you'll most likely use an arrow, but in math you'll just use these, just the abstraction of all vectors. Because in physics you don't need, usually I guess, to go to like 5,000 dimensions, but in math you need to get to every possible thing often. So as soon as you like get all possible vectors, you are just messing with every dimension at once. Okay. So there's no real right or wrong way to define a vector, just depends on what you need. Subsection vector equality addition and scalar multiplication. Alright, let's go. Two vectors to be the same. Okay, so if all their numbers are the same. Yes. Symbol equals to now doing triple. Why? It's for two numbers to be equal. Yes. So means two sets. Yes, but yeah. It's not really a problem though. Because it's not sort of equality you have encountered. Well, they are all pretty similar, so yeah, you can do 3 equals 1 plus 2 anyway. Then make this equal like the same equal as in a set A is equal to 1 red. I don't know whatever here. Because numbers are also sets by some definition, so yeah, I don't know what's the point of this. Two objects are equal. If you have definition CVE Or you could link it here like everything else. This is employed. Oh wait, no, just do. Okay, let's see. Uh, what even is CV? Oh no, I've forgotten every acronym. Okay, an example. Vector equality, a system of equations. Okay. Signs indicates an equality of numbers. Now write the vector equality. This. So by definition, CV, the single equality, translates into three simultaneous equalities of numbers. Yes. Yeah. So with this new notion, yeah, because of course, this means that this is equal to that. Yeah, by definition. There's more to vector equality than just this, but this is a good example for starters, and we will develop it further. We'll now define two operations on the set C to the m. Okay. Define procedures that somehow convert vectors into other vectors. Alright, yes. So addition. How does addition work? You just add every number, right? Yes. So you add every number. That is the required. Even if we agree this is the obvious, right, natural way to do it, yes, but it has to be defined, of course. Symbol plus being recycled, yeah, it's the same. So this is definitely. Think about your objects, especially when doing proofs. Vector addition is easy. Here's an example from complex to full. Okay, well, C. So I don't know how I should call this. C to the m, C to the 4 here. Okay. Addition of two vectors, so you just add every number. Right, so yes. The operation takes two objects of different types, specifically a number and a vector, and combines them to create another vector. In this context, we call a number a scalar in order to emphasize that it is not a vector. Alright. Column vector scalar multiplication. So, yes, you just do that. Yeah, I know how this works. We're doing for a new type of multiplication. Yeah. Here's a lowercase Greek letters. There's some hints of what alphabetics we're working with. Yes. Okay, okay. There's no vector scalar multiplication is very easy. Well, yes, it is. So you just multiply everything by this alpha, and that's it. Okay, so, ooh, what's this? Oh, yeah, some properties, which I don't think they prove everything. Yeah, there's a lot here. Okay, so let's see. We can 10 of them. Okay, which of course are acronyms. Surely, who wrote this? I thank you for writing this. I mean, it's a pretty good PDF, but come on. Mm, so, ACC, wait, plus complex numbers itself. Yes, so these are the properties. If you need an U plus V are vectors, of course. So they are closed under addition and closed under scalar multiplication. Yeah. Plus b equals b plus u. Zero vector. Yes. Zero vector. Scalar multiplication again. Okay, makes sense. Alpha is, let's see. Wait. Distributivity across vector addition. Yes, alright. Makes sense. This is the same. Oh no, this isn't the same. Wait. This is the same. No, this isn't the same. But yeah. And then 1 equals u. I mean, yes. Yes, of course. Of course it does. Uh, okay, proof. Well, some of these properties are pretty obvious. They don't require. Are you going to prove every single one of them? Conversion of distributivity. Be very careful when you contest your proof building skills with some of the other. I'm not even going to read this. I don't care. This is, well, no, it's pretty simple. Alpha plus, yes. So this equals this, right? So close that. Then what? Going with some properties. One property here. Wait. Wait. Yes, I mean, sure. What? Yeah, I don't care. I don't care. Cheers. This is trivial. So yeah, because that. Since the individual components of the vectors alpha plus beta u and alpha u plus beta u are equal for all I in 1 and m, then, oh yeah, this is the proof. Many of the conclusions of our theorems can be characterized as identities, especially when we are establishing basic properties of operations such as those in this section. Most of the properties listed in theorem are examples. So, wait, what? What's this theorem? After property, yeah. Mm, okay. The proof technique P. Okay. 93. Right. Yes. Okay. Let's see what's this. Proving identities. Is a path start. I mean, yeah. What's this, bro? Many have conclusion that say two objects are equal. Perhaps one object is hard to compute or understand, while the other is easy to compute or understand. To make it for a pleasing theorem. Indeed. Okay, so by writing it down and then beating on it until it reduces to an obvious identity. Wait, really? Wish to prove. As if you already believe this to be true. Oh, alright. Well, that makes sense, yeah. There's a possibility that some of your maneuvers are not reversible. Alright, everything has to be reversible. Yes. I mean, the mistake here is that the square maps, like, squaring something maps, like, two numbers to one here. It's not a bijection, so Of course, if you're doing this, yeah, then you have 3 and -3, and this ends up here, and this ends up here, they end with the same number. If you try to reverse it, then you get this, and you won't get the other half of the, because then it wouldn't be a function. So, yeah, that's a problem here. Wait, no. Let me see. To prove that a equals t, we'll write, okay, so that's, well, yes, I'm just do stuff in the right side. I mean, I've seen this enough times, so I understand that this is how it's usually done. I guess you could also do this, but then write it like this, and if you can't write it like this, then you can't reverse, you can go like this, and then go up again. So yeah, that's, I think that would be, I don't know, probably. And your crosswords now. Okay, okay. This is a variety of expressions. Let's take a line of attack. Write your proof carefully, mimicking this style. Okay, that. I mean, this is linear algebra, but I see that this has some stuff about proofs, even though it's not proof theory. It should be in proof theory, but hey, it's useful, so yeah, it's cool. Okay, 93. Let's go back to this. And, okay. Um, where are we? Proof this. Many of the conclusions of our theorems can be characterized as identities, especially when we're establishing basic properties of operations such as those in this section. Sorry. Most. Mm, wait, this is the first thread. So the vector negative u. Vector addition. So we can put it in the other operation. Yes. It's just the same. Oops. Oh, 93. So yes, and we will see later how to derive this property as a consequence of several of the 10 properties listed in that theorem. Vector subtraction, well, it could be defined from the addition, or that, I guess. Yeah, sure. Okay, fine. We're writing, yeah. This, but yeah. In parentheses, this way. Okay, so questions. The basics about vectors. Is the introduction to vectors. Okay, so we're almost in page 100, by the way. Not here, but well, almost to infinity. It's pretty nice. Where have you seen vectors used before in other courses of physics? How were they different? They were errors. Universally, when are two vectors equal? When all of their members are the same, all of their numbers inside are the same position, and yeah, the same in the same position, and the same number of numbers, of course. perform the following computation with vector operations. Yeah, that's compute. So the equation for x, explain why no solution exists. Okay, this is irrelevant. This is irrelevant. I mean, these two numbers up there are irrelevant, so it matters the -3 plus 4x equals 17, and you solve for x. Here you solve what this system of equations with 3 equations and 1 variable. So hope that it works for every equation. And same here. And now it has 2 equations. Systems of equations. What? This is like, you know what we've been doing with matrices, but they're different. Okay, now we get to the C. Ooh, and theorem and proof, and theorem and proof, and theorem and proof. T, the T challenge. Okay. Provide reasons, a justification for each of the 7 steps following this, the following proof. What is it? Oh, so there are, okay. Suppose u plus v equals u plus w. Then u equals, no, then v equals w, right? That's the conclusion here. Oh yeah, it says it here. So 0 plus v, yeah, this is a property. This is another property, distributivity. U plus v equals u plus w according to this. So yeah, that's another property, but it has to, and then you get it back here, and yeah, it's the same. 0 u equals 0. Okay, so 0 equals, yeah, multiply these by number, of course. Thing. 0 equals 0. Okay. For any scalar c, c times 0 equals 0. Is that really like vector stuff? Doesn't even use vectors. Yeah, sure, okay. It's the same thing as before. Oh, there are more. Proof properties? No, I'm not going to. Subtraction. Or that, yeah, sure. Do that. Two vector operations. Yeah, I should just did it here for me. Proof by giving counterexamples that vector subtraction is not commutative and not associative. Well, I could, but I won't. So I have to write for that. Okay, section linear combinations. Combined to give us a construction known as a linear combination. Construct that we will work throughout this we will work with throughout this course. Nothing, my English pronunciation sucks right now. Given n vectors, u1, u2, u3, un. The linear combination is the vector of this. Scalars and vectors. Combines them using 2 new operations. The combination is pretty easy. Yeah. 2 linear combinations. Yeah. You have this, for example. You have all this. you got this vector, which is a linear combination of all of these. And we'll do the same again with another one. You could create the vector W with a suitable choice of 4 scalars. I don't know, maybe. Probably not. So I know this has... How many vectors do I have? 4? I have 4 vectors. So yeah, probably not. Most likely not. I know, but if it's like you put these all in the matrix and it's like a rank or like all the vectors are linearly. If you have 6 linearly independent vectors, yeah, but I have 4. Don't even have 6 vectors, so I can't do almost any of these. Okay, so 98. Our next 2 examples are key ones. Any discussion about the composition is timely. Okay. Next 2 examples. Okay, what do you want me to see? DC. 98. The composition. Study of algebra. Well, simplifying expression. Combining like terms. In common denominators so as to affect. I'll just read this silently and start talking again later, I guess. The simpler expression, right? Yeah, of course, man. As you can see, of course it is simpler, man. Yeah, come on, quick. What's the domain of this? The main f of x is equal to this. What's the domain? Simple. Okay, so yeah, it just depends on what you want, really. Okay, let's go. 98. Where was I here? Okay. How could I be as a linear combination? So, okay. This example for a language of vectors, equality, and linear combinations. Now we will bust up the linear expressions on the expression like this. Okay. Scalar multiple. Ooh, nice. That's pretty nice. Then the problem solving the system of determining values for each of the scalar multiples and make the vector equation true. Okay. I mean, it's pretty much the same for now, so there's nothing really special here. Uh, okay, so yeah. You find the solution, but you find it with matrices. Okay, let's see what this adds. Um, mhm. Of course. So let's see how the three vectors in this axiomatic comes. Wait, so this is a linear combination of all of these three. This is our first thing of important interplay between the vectors that form the concept of a matrix and the matrix itself. Yes, they are the same, basically. So I guess they are pretty similar. With this, okay, now the archetype A. Mm, okay, and you got this. The matrix, okay. Alright, it works. Yeah. But ignore the middle of the equation. Wait. Wait a second. So you oh so this is zero. No wait, this isn't zero. What? Oh right. That is a non-trivial solution of the homogeneous system of equations. The coefficient matrix. Oh, that this coefficient matrix is singular. Hmm. Nice. So if there are more than one solution, there's more than one solution, then the matrix has to be singular. So yeah, you didn't prove it earlier. This didn't really prove it earlier, so yeah, now that concludes that part of the proof, I guess. Or was it the other direction that it didn't prove? I don't know. Eh, I don't know. Um, with the intervening material, okay. Let's summarize and explain. Okay, so page 100. Perfect. page 100. Come back. Wait, now just do it here. There we go. And let's keep going. Okay, so we have this. So B is the vector, yes, B is the vector. Equals the linear combination of the columns of A front. Yes, yes. Well, is this where matrix multiplication comes from? I don't remember it exactly from like 3 blue 1 brown, so I don't understand this button here. It's really weird. Those 44, does it mean they are, wait, I don't even understand most of this. Okay, okay. Is everything here okay? Yes. Apparently, yes. Okay, everything is okay. So, back to this. Okay, so, okay, this makes sense. Alright, so, notation, yeah, it's just a, it's really just the same thing. Question asks that. Notice that, notice then that the entry of the coefficient matrix, coefficient matrix A, row I, con J has two names. A sub ij and that other one. Okay, so I want the I of B has two names. Proof of there, okay. I don't think I need to see this. This is just like changing notation, so I'll just give this. Another word is so just the systems of equations are linear combinations of the n column vectors of the coefficient matrix A sub j, which yield the constant vector B. The vector B is a linear combination of the columns of A. Yeah, say column, say linear combination. Let's see. Okay. So yeah, I won't verify that. I, there's no need. Mhm. We realize this. When solutions to system as column vectors. Now we will use column vectors and linear combinations to express all of the solutions to a linear system of equations in a compact and understandable way. Hmm. Okay, so a new technique. Okay, let's see. What's this? Well, let me just read this again now, just in case. Uh, Alright, yeah, let's just go. Vector form of solutions for archetype V. Archetype V, okay. Using the argument, the augmented matrix yields this. Yeah, this. Uh, so R equals 2 and this, so yeah, this is so what's it on solution vector. Oh, yeah, equation for dependent. Okay, so we got this vector, this new vector, this is the solution vector, and of course, plus this, put into what we will do here. And we will use the features column vector addition and scalar multiplication to express this vector as a linear combination. Why? Okay, so okay equals to 4 and then there's the x sub 2, which then wait, no, it's just removing this one, then the x3s and the x4s. Okay, and the ones without, well, without x, without variables, and okay, in 3 steps. Okay, I prefer the approach. Okay, tell me, write the vector variables as a fixed vector. So a combination of n minus r vectors, and the free variables as the scalars. Okay, so this vector, and then we have these 3 vectors. Use zeros and ones to ensure the equality for the entries of the vectors with indices in F, corresponding to the free variables. Exactly, okay. Wait. So x3 equals, yes, this and this, okay. You don't even need to look at the matrix. Step Step 3. For each dependent variable, use the augmented matrix to formulate an equation expressing the dependent variable as a constant plus multiples of free variables. Convert this equation into entries of the vectors that ensure equality for each dependent variable. One at a time. So you have x1 equals to this. So you put the x1, the x1 split and add, well, 1 without x, get a 4. And you add negative 3 here and 2 here, okay? And same with the x sub 2. Okay, fine. Why did I get pinked? Senko bread. Senko bread says Senko bread V3 says good stream. Thanks, Senko bread. Why are you watching on YouTube or what? Maybe, I don't know. Okay, let's see where we are. So this is just do the same thing here, and final form is a typical solution. Typical solution is especially producing and useful. Well, yes, just you can just replace the x3 and x4, and that's it. Quickly by choosing values for free variables, any value by the way. So it's really easy. You compute a linear combination, such as this. X equals this equals well, this plus that with the numbers, and that's it. Really easy. You will find the second solution listed in the right. You might try the first solution by substituting it back into the original equations. What every solution looks like. Another solution says infinite. And also, you also knew the solution set is infinite by making it a set. But yeah, this looks more like clean. And we can see that solution is a multiple. Oh yes, multiple of this plus a multiple of this plus the fixed vector that. Period. So it only takes us 3 vectors. It only took 1 before. Well, yeah, this is cleaner, like simple numbers. There's but we also agree on how to combine the 3 vectors into a linear combination. It's an important fundamental technique. We will do another example and with a fucking massive matrix. It's an important and fundamental technique. We will considering a system of m equals 5 equations in n equals 7 variables. In the augmented matrix A, this 1, 2, 3, 4, 5, 6, 7, yeah. Then we obtain the matrix this. Okay, this goes away. That's 4 pivot columns. So if I see the primary variables are then 10, 1, 2, 5, 6, and 3, 4, and 7. Okay. This produces the generic solution for the system by 2 different methods, both a decomposition and a construction. Okay. First, we will decompose. Oh, yeah, never mind. Decompose a solution vector. So this, okay. Vector, you use this. That's it, and now you, or you can do the other step, of course. Where the free ones, these ones, 3, 4, and 7. Good. And now you do this with the matrix of these steps until it's full. Okay. Fine, so you choose 3 numbers, you can make the solution. This or that, okay. Wait a moment. Okay, fine. You were told that the vector W below was a solution to the system of equations. Could you turn the pointer around and write W is a linear combination of the 4 vectors C, U1, U2, U3? The vector W below was a solution to a system of equations. Oh, well. So you have to find like the x for the vector u1 you have to find the x3, for u2 x4, and for u3 x7. You have to okay, wait. So you have u1 times, no, you have I'll do it here. So this is basically finding like a making it another system of equations. Yeah, this is making it another system of equations, basically. So if you do this, equals to c plus x2 times, no, x3 times u1 plus x4 times u2 plus x7 times u3. So if you do this, yeah. If you do this, you are basically just get this here, w minus c. Right, I think. And now this is another system of equations. This time you have 3 variables and 7 equations. So I guess you can do that. Why not? Okay, so let's go. Okay, so we'll now formalize that there's two examples as a theorem. The statement in this theorem is a bit scary, and the proof is scary. Oh no! Please stop! Please no! Please don't be scared. Than this, than this, please. For the love of God, please. Just no. I mean, come on, look at this shit. Okay, let's see. Let's go for it. You can do it. Um. So suppose that A was the augmented matrix. Okay, for a consistent linear system. Whether here. Okay. Wait, there's a. Okay, so of m equations in m variables. So let be row equivalent matrix in the reduced row echelon form basically. Suppose that B has R pivot columns. Okay. This is the F set. Define this is just a statement. Oh my god. I don't want to look at the proof. I have to look at the proof. I thought this was the proof, but it isn't. Okay, Find vectors. Define vector C u sub j. C and u sub j such that j is between 1 and n minus r. Sort of size n by this. So if I is in F, if this, you fucking can. Bruh. Bruh. You're kidding me. What is this B? Okay, this B is the reduced row. No, yes, this is the row echelon form. The reduced row echelon form. Okay, so let's see. C sub I is equal to 0 if I in F. And B. Oh, I see, I see, I see, I see, I see, I see. Okay, 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 okay. It's not. It's okay. It's okay. B sub k and sub k n plus one. Okay. B sub k n plus one. If I is a member of V, so I said I is equal to vk. This is sub k. Okay, so if I is a member, I being this sub k. Okay, okay. Let's be k. Wait. Oh yes, yes, yes. K n plus one. Okay, okay, okay. Oh, wait. I think I get this. Probably. Okay, so that's the vector C. And U, all the U's, U sub J, for a bunch of J's. Then, that's 1 if I is an F and I is equal to F sub J. Okay, yes. 0 if I is in F and it's not equal to F sub J, okay. And negative B sub K F sub J. if I is a member of D, I equals D sub K. Okay, 1 second, let me process this. Alright, fine. Wait, this is page 109 and alright, yes. Uh-huh. Okay, okay. And the set of solutions to a system of equations is C plus alpha 1 U1 where all of the alphas are complex numbers. Any complex numbers. Okay, that wasn't even the explanation. That was just the statement. So basically, what it's saying. Okay, I'm a bit slow with this. I'm sorry, I suck at math, I guess. But this is basically what was happening earlier. So you have wait. Okay, 1 second. So you have the vector C. It's like okay, let's actually get the massive vector. So you have the independent variables just like that, with all the dependent variables stuff. The dependent variables are just themselves. Okay, independent variables like that. Okay. So when you reduce it, well, when you like make it several vectors, this is the C. Let's say this is some U J, right? U sub J. Some U sub J. So with U sub J, okay, so C is the numbers that don't have any variables. And so that's basically like the last column. So this is what it's doing. This is getting the last column, the augmented part of the matrix. And all the U sub j's are, well, for the for the dependent, no, for the independent variables all 0, except for the one it corresponds to, which is a 9. And then like when you get the matrix, and it's like that, and you get the reduced echelon form and pass all these numbers here, and that's negative numbers you get here. So yeah, I don't think anyone will understand just with the explanation. Yeah, let's just go. Proof, bruh. Okay, let's go. First, ls equal ls is equivalent to the linear system of equations that has the matrix B as its augmented matrix. So we need only show that S is a solution set for a system with B as its augmented matrix. Okay, so S is this. Wait. According to this linear system of equations that has the matrix B. Okay. We need only show that S is a solution set. So this is the same as the solution. Okay. Is that the solution? Well, to set S, so we will apply definition. We begin by show. Okay, wait. I want to see what it was. set equality. Uh, that How long has this stream been going for? 9 hours already. Almost. Alright then. Alright then, so where was I here? Okay. I guess maybe I'll finish this and I don't know, do some, I don't know what page I'll get to, and then I'll restart the stream. Okay, so proof. First, we begin by showing that every element of S here is indeed a solution to a system. Okay, yes. So let alpha, all the alphas be one choice of the scalars used to describe elements of S. Element of S, which we will consider as a proposed solution, is that okay equals that. Yes, basically when r plus 1 is then or equal to L, row L of the matrix V is a zero row. Okay, so the equation represented by that row is always true no matter which solution vector we propose. This is centered on rows representing equations from 1 to r. We evaluate equation L of the system represented by P of the proposed solutions V and X. Refer to the value of the left-hand side of the equation as V as beta sub L. So beta sub L equals that. Well, yes. Since beta sub L equals 0 for all from all 1 to R, and that then this simplifies to wait, what? I don't understand anything here. Oh, Dr. Cock. Dr. Cock. Check this out. Okay. Wait, no. Okay, so entries of X and wait, now where was I? When CV? Why do I need this? I wasn't here anyway, so okay. So when R plus 1, okay, I might spend half an hour in this, just on this. Seriously, are you kidding me? Where's the words in my... Okay. We begin by... Okay, we begin by... I just read it again. Only one choice of the scalars used to describe elements of S. So an arbitrary element of S is this, right? Okay, that makes sense. Yes, yes. When R plus 1 is equal to M less than or equal to M less than or equal to M, row L of the matrix B is a zero row. Row L of the matrix B is a zero row, yes. So the equation represented by that row is always true, yes. So concentrate on rows representing, okay. from 1 to r. Well, the equation L of the system represented by P with the proposed solution vector x. Okay, we evaluate equation L of the system represented by B with the proposed solution vector x, and refer to the value of the left-hand side of the equation as beta sub L. So beta sub L is equal to B of the system represented by B. Alright, wait. We evaluate equation L of the system represented by B with the proposed solution vector x. Yes, just the alphas, right? Well, the alphas times, okay. And refer to the value of the left-hand side of the equation as beta sub L. Refer to the value of the left-hand side of the equation as beta sub L. So beta sub B sub L1. Okay. So this is 3x. Wait. Okay. Since v so vi equals 0 for all 1 r except this one, of course. Beta L simplifies to this plus all the f's. Notice that for I between 1 and n minus r, we have this. Okay, f sub I. Wait. Notice that for 1, so all I between 1 and n minus r, so I, x sub f I is equal to this. So CF1, no, F alpha 1, yes, that, which is equal to, okay, F sub I, okay? So, 0, why is this 0? I don't understand, why is this 0? C, so C is 0. And alpha 1, oh, this is all 1, all, I come from though. Oh, okay, okay. Oh, okay, we were in the F. Wait, were we? Is this really needed? Come on. 109. 100. Theorem BFSLS. And as soon as this gets to this. Wait, what's going on? Wait. Wait, what's going on? Is this good now? No, it's not. What's going on now then? Okay, it's good now, so is this good now? It's almost at 9 hours, so I should just end it soon. Soon enough. Okay. Okay, I'll end it soon enough. And restart it, of course. I'm going to restart it immediately. This is fine. This should be fine. Why isn't it fine? What's going on? I don't understand. Chatter, what's this? Playbacks. Sure, whatever. Okay, yeah, just yeah. Oh, excellent connection now. Fine then. Hmm. So I just skip over this. Oops. Oopsie. Okay, here it goes. Finally. I'm sure there has to be a simpler proof, please. We know that both halves of the proof of theorem make it a sub I, alpha sub I. I should have more meaning there. Free values of the variables x of f fi. So yes. Okay. This completes our conversion of linear equation solving from art into science. Seriously, we weren't done before. I mean, yeah, after this, I hope it is. It even applies. Vertical in the case of a unique solution. Oh, please. The practical matter, I prefer the three-step process of an example. Yeah, if there's current field solution set. Let's practice some more with a bigger example. Okay. Well, I have actually done 100 pages like this in 9 hours. Well, not yet. I'm not in page 100. I'm not in the ninth hour either. So I might actually get to page 200. It's not bad. Okay, so vectors. Mhm. 'Wait, so all right, so 2, 5, 6, 7. 2, 5, 6, 7. The x sub 2, sub 3. Yeah. So 5, so 6, so 7. Oh yeah, this is the same. So 2, 5, 6, 7. You did this. For each dependent variable, use the augmented matrix to formulate an equation. So yeah, this is 4, -4, -2, -1, and 3. Okay. And same here with all the numbers, and that's it. Okay, so can I use the functions to the system? Yes. Like by substituting the x's. Okay. Definition of the finished solution set. Five vectors which we combine linear combinations to produce solutions. Yes. And this is the same it said before. The 0, 1 pattern at the conclusion. Yeah, it's easiest. Creates all zeros and then 1, 1, 1, 1. Going down each time. Have fun. No, I'm not going to do archetype J. Again, hold the archetype J. I'm not going to do this. Where was archetype J? This technique is so important. We will do one more example. Oh, with an important distinction. Oh, this is homogeneous. Okay. So, okay. Vector forms that L. So, Do you remember the missing six column of zeros? Mm-hmm. I think it's lost, yeah. Okay. And now, okay, so we use this. No, okay, so this will be 0, 0, 1, 0, 0, 1, right? Yes. Variable is the augmented matrix. The formulate an equation expressing the dependent variable as a constant plus multiples of the free variables. Let's forget the missing sixth column being full of zeros. Okay, so yeah, this is all zeros. And well, yeah, just fill these. Mm-hmm. All C are all integers are zero, so yeah, C equals zero. Yes, of course. In the case of a unique solution, yes, yes. So our expression for the solution is a bit more pleasing. This example, yes, you can just remove this. Oh yeah, like this. All possible linear combination of the two vectors. Mention of any fixed vector entering into the linear combination. Okay. What the hell is this? We'll do the next section and the main definition of that section after that we will conclude the section by formalizing the situation. Okay. Let me check again. Is this 6 more minutes? What's going on here? 6 more minutes. Hmm. So 53, okay. Well, this observation will motivate our next section. Okay. So the next theorem tells us that in order to find all solutions, wait. Do I have time for this? Maybe. Yeah, it's not that long. Can't be that hard, I guess. Next theorem tells us that in order to find all the solutions to a linear system of equations, it's sufficient to just find one solution and then find all the other solutions to the corresponding homogeneous system. Wait, what? We need to find all of the solutions to a linear system. We need to find one solution and then find all of the solutions to the corresponding homogeneous system. Okay. Okay, so suppose that W is one solution to a linear system of equations, then Y is a solution to that if and only if Y equals um, W plus C for some vector in the null space. For some vector C in the null space of A. Okay. Okay, I see. I mean, yes. Makes sense. Makes sense, yeah, makes sense. Prove that A1 is with the columns of the coefficient matrix A. And suppose Y and okay, so B is equal to this to so wait B is equal to this. okay, it's the okay, yeah. W is W. Wait. A and the columns. Okay, so this is a solution. That was just one solution. Okay, yeah. This is a solution, and these are the columns. Okay, F0, which becomes this 0. It's the solution to the homogeneous system, so this is 0. This is okay. So you get all of these. So you get the addition of all of those. And oh, addition of y. This is y. Of course, yeah. Okay. We see that the vector y is a solution. Okay. Oh, it's an infinitely. So suppose y is a solution to that. Then 0 is b minus b. So this solution minus this other solution, which are both the same, of course. So this is equal to y minus w. 0 equals y minus w. And so the vector 1 is the solution to the homogeneous system. So it's in null space. Okay, correct. This is correct. This wasn't that hard. Okay, so might be getting to the end of this. 9 hours, so that's it for now. I'll end and just instantly come back. Okay.